The first glimpse arrived quietly, almost unnoticed, through the lens of a telescope trained on the vast, indifferent expanse of the night sky. In the empty stretch between Mars and the asteroid belt, a faint point of light shimmered, subtle yet distinct, moving along a path that seemed to mock the carefully calculated motions of planets and known asteroids. At first, it was catalogued as an ordinary visitor, a wandering piece of cosmic debris, another shard in the endless collection of objects tracing predictable orbits around our Sunday. Yet, even in those earliest frames, a tension lingered in the data, a suggestion that this object refused to be neatly understood. Its trajectory did not conform to familiar celestial mechanics. It was unlike any asteroid, unlike any comet. It carried with it a sense of arrival, of trespassing, as if the universe itself had sent an emissary whose intentions were unreadable, whose origins were unknowable. Astronomers across continents, many seated in remote observatories under frigid, wind-swept skies, began to whisper among themselves. The discovery was initially classified as 3I Atlas, a name dry and technical, yet it masked the quiet terror of the unknown. In the sterile charts and logs, a strange beauty emerged. The path was hyperbolic, not elliptical, signaling that this was not a mere resident of our solar system, but a traveler from the interstellar void, a messenger from realms beyond our immediate comprehension. There was poetry in its motion, a deliberate grace in its defiance of gravity's familiar cadence, yet beneath the poetry lay a subtle disquiet, the unsettling sense that we were witnessing something both extraordinary and inexplicable. And then, just as the human mind began to settle into a rhythm of observation, something unprecedented happened. Additional points of light began to appear near 3I Atlas, like sparks igniting along a hidden wire in the cosmos. They multiplied not linearly, not gradually, but with a pattern that resisted casual explanation. Telescopic surveys, initially intended to track a single object, revealed a small swarm of companions, faint but undeniable, each following trajectories that hinted at both connection and independence. The first reports were met with disbelief, a hesitation born not of skepticism, but of the audacity of the universe itself. How could one interstellar object be accompanied by others, multiplying in a manner that defied the ordinary rules of celestial formation? The early photographs were grainy, faint dots smeared across the frame, yet they conveyed a clarity of intent. These were not random debris. The multiplicity suggested a phenomenon that challenged conventional astrophysics, hinting at a process or event that humanity had yet to witness. Was this the shattering of a larger body, fractured by forces beyond our imagination, or was it something entirely different? A cascade of small interstellar travelers released from a distant and ancient source. Each scenario carried with it both scientific fascination and a deep, almost existential unease. The cosmos, vast and indifferent, had produced a tableau that blurred the boundary between discovery and confrontation. In laboratories from Hawaii to Chile, from the deserts of Arizona to the frozen plains of Siberia, researchers convened. Data streams illuminated screens, graphs plotted the unpredictable paths, and equations sprawled across whiteboards, but the pattern refused to submit. Computer models, calibrated against centuries of celestial mechanics, failed to replicate the observed multiplication. The swarm was simultaneously connected and chaotic, moving in a manner that suggested hidden rules, subtle influences, or phenomena entirely beyond the scope of current physics. Observers began to feel the weight of incomprehension, the strain of trying to fit the extraordinary into frameworks built for the ordinary. Yet, the emotional resonance extended beyond mere professional anxiety. For anyone who paused under the night sky, the image of multiplying objects near Mars evoked awe and unease in equal measure. There was a profound loneliness to these points of light, a sense that the universe held secrets inaccessible to human perception. And still, a subtle poetry lingered. The objects traced their paths silently, elegantly, each dot a testament to forces that predated humanity, to cosmic processes that would continue long after our presence had faded. Their movement was a meditation on distance and time, on the thin line between order and chaos, a celestial choreography indifferent to human observation, yet capable of inspiring reflection on our place in the universe. The suspense was not only scientific, but deeply philosophical. Here was evidence that the cosmos was not static, not merely a predictable machine, but a living canvas capable of surprises, of multiplication, of unfolding narratives that intersected with our solar system without warning or explanation. The objects seemed to gesture toward questions that had no immediate answers. What is the nature of interstellar travel? How many forces operate in the space between stars that we have yet to detect? And, perhaps most unsettlingly, what does it mean for humanity to witness the unexpected multiplication of such entities, so far from home, yet suddenly pressing against the boundaries of comprehension? In these early days of observation, as astronomers double-checked coordinates and recalculated orbits, the sense of mystery deepened. 3. I-Atlas was no longer a singular phenomenon. It had become a herald of multiplicity, an emblem of the unknown. Its companions, emerging like faint brushstrokes across the cosmic canvas, demanded attention, reflection, and humility. And, while the numbers, orbital velocities, distances, spectral readings would dominate scientific discourse in the coming weeks, the immediate, visceral impression was one of awe. Humanity had glimpsed a fleeting, multiplying signature of a universe both vast and enigmatic, and for the first time we felt the simultaneous exhilaration and terror of encountering an interstellar mystery in motion. As night gave way to the slow, tentative light of dawn across observatories, the first reports circulated widely. Scientific bulletins, usually dry and measured, carried a sense of urgent fascination. The telescopes had revealed not merely an object, but an event, a process unfolding in silence, light years from home, yet suddenly pressing against our understanding. It was a call to attention, a reminder that the universe was far from a settled story, that interstellar phenomena could arrive unannounced, defying expectation and inviting both wonder and fear. And in that quiet, contemplative moment, as astronomers and casual stargazers alike traced the faint points of light across dark skies, the emotional gravity of the discovery settled in. This was no ordinary passage of a solitary object, but the opening act of a cosmic narrative whose full meaning would remain elusive, poetic, and profoundly unsettling. The discovery of 3I Atlas did not happen in isolation. It emerged from the patient vigilance of astronomers who had trained their instruments on the heavens for years, seeking to map the familiar while remaining alert to the unexpected. The initial detection occurred through the All-Sky Automated Survey for Supernovae, a network of robotic telescopes designed to monitor transient events. On that quiet night, amid the routine tracking of known asteroids and comets, the survey recorded a point of light moving along a path that seemed foreign, almost deliberate, in its defiance of expectation. At first glance, it appeared as another small solar system object, a passing fragment, an unremarkable visitor, but careful calculation of its velocity and trajectory revealed something extraordinary. Its path was hyperbolic, not bound by the sun's gravitational embrace, suggesting an origin far beyond the familiar neighborhood of planets and asteroids. This initial observation was soon confirmed by multiple observatories, from the remote peaks of Mauna Kea in Hawaii to the Cerro Tololo Inter-American Observatory in Chile. Astronomers combed through archival data, attempting to trace any prior appearances of the object, but 3I Atlas had seemingly emerged from the void without precedent. The recognition that this was an interstellar object, not merely a local asteroid, ignited a flurry of excitement, curiosity, and meticulous scrutiny. In the sterile calm of research labs, scientists pored over orbital parameters, plotting its trajectory with the precision demanded by physics, aware that even minor miscalculations could obscure a truth that was already unsettlingly clear. The universe was sending an uninvited, mysterious visitor into the inner solar system. Key figures emerged in the unfolding narrative of this discovery. Astronomers at the University of Hawaii, who first flagged the object, were joined by planetary scientists and astrophysicists worldwide, each contributing specialized knowledge to a collective effort. Observatories linked across continents, sharing images, measurements, and spectral analyses. In their collaboration, one glimpsed the human dimension of cosmic exploration, the shared wonder, the intellectual rigor, and the quiet awe of confronting the unknown. Each observation, each calculation, each plotted point on a graph represented hours of patient labor, a testament to humanity's persistent desire to understand the vast and indifferent cosmos. As 3I Atlas approached Mars, it became apparent that the object was not solitary. Follow-up observations revealed additional points of light in proximity, faint companions whose presence complicated the initial narrative. These were not typical fragments resulting from solar system collisions, nor did they correspond to known orbital debris. They appeared to multiply, subtly at first, then with increasing clarity, forming a small cluster that demanded explanation. The emergence of these companions elevated the sense of mystery. What mechanism could produce multiple interstellar travelers in close association? Were these fragments from a parent body shattered in some distant event, or did they originate independently, converging by chance? The scientific imagination stretched in multiple directions, constrained only by the limits of evidence and the laws of physics as currently understood. The instruments themselves told stories that added layers to the enigma. Ground-based telescopes, equipped with sensitive CCD cameras, captured the faint movement across the sky, recording each object's brightness, speed, and apparent composition. Spectroscopic analysis revealed subtle variations in albedo and chemical makeup, hinting at unusual combinations of rock, ice, and perhaps materials not commonly observed in solar system bodies. Every new data point deepened the mystery rather than simplifying it. The consistency of hyperbolic trajectories, the multiplicity of objects, and the spectral anomalies combined to form a profile that defied standard classification. 3I Atlas and its companions were not merely travelers, they were outliers, exceptions to every pattern astronomers had learned to trust. The early scientific discussions were cautious but tinged with excitement. In private conferences and correspondence, astrophysicists debated the reliability of initial observations, the potential for instrumental error, and the implications of the hyperbolic paths. Yet, as additional measurements were verified, the consensus grew in confidence. The phenomenon was real, and it was unprecedented. Historical analogues, such as Oumuamua and Comet Borisov, were considered, but none displayed the apparent multiplication observed here. The human mind struggled with the scale of unfamiliarity. Centuries of celestial observation had prepared astronomers to identify solitary interstellar objects, not a small swarm multiplying as it entered the inner solar system. The narrative of discovery was further enriched by the collaborative ethos of modern astronomy. Teams spanning continents, cultures, and specialties shared data through digital platforms, connecting the scattered nodes of observation into a coherent network. Each telescope contributed a small, precise perspective. Each researcher added context and analysis. This global collaboration illuminated the meticulous choreography behind cosmic discovery, revealing that even in the face of the unknown, human inquiry could produce clarity, if only through patience and shared effort. Beyond the technicalities of measurement and trajectory calculation, the discovery carried an emotional weight. Observers reported a mixture of awe and trepidation. The sky, so familiar and mapped, suddenly presented an anomaly, reminding humanity that even the most closely studied regions of space could harbor surprises. The multiplication of objects near Mars was not merely an astronomical puzzle, it was a confrontation with the unknown, an invitation to question assumptions about the predictability of the cosmos. In the silent observatories, beneath the sweeping darkness of desert skies or the frigid altitude of mountain telescopes, scientists felt the thrill of discovery intertwined with the humility of recognizing that the universe operates on scales and with mechanisms far beyond immediate comprehension. Meanwhile, as 3I Atlas drew closer, predictions became increasingly urgent. The orbital mechanics were recalculated, the gravitational influences of Mars, Jupiter, and the Sun modeled with higher precision, and simulations were run to forecast potential interactions. Every iteration underscored the object's anomalous behavior. The paths of the newly discovered companions did not correspond to standard n-body dynamics, suggesting influences not immediately apparent, subtle accelerations perhaps, or unknown forces at play. Each confirmed observation strengthened the reality of multiplication and the need for rigorous investigation. In reflecting on this period, one sees both the human and cosmic dimensions intertwined. On one level, it is a story of instruments, graphs, calculations, and coordinates, a technical triumph of observation. On another, it is a story of anticipation, of humanity's collective gaze lifting to the sky in wonder and suspense, attempting to understand visitors from the vast reaches beyond. The interplay between precision and mystery, between careful measurement and profound uncertainty, defines the discovery phase of 3I Atlas. It is here, in these earliest observations, that the first threads of the narrative are spun, threads that will weave through anomaly, theory, and reflection, drawing the viewer deeper into a story where science and philosophical contemplation meet, where every faint point of light carries both data and the weight of the unknowable. As the days progressed, the network of observers and instruments continued to refine the object's characteristics. The faint companions became more discernible, their movement increasingly resolvable against the backdrop of stars. Each new frame of data added complexity, revealing subtle variations in speed and trajectory that hinted at interactions or influences yet to be identified. The atmosphere of scientific vigilance intensified, with nights spent cross-checking coordinates, ensuring calibration, and maintaining continuity of observation. The careful patience of discovery, the slow accumulation of certainty amidst uncertainty, established a foundation for the deeper investigations that would follow, framing 3I Atlas, not merely as a point of light, but as a phenomenon with the power to challenge understanding, to inspire reflection, and to provoke both scientific and philosophical curiosity. As astronomers continued to monitor 3I Atlas, a startling realization emerged. The object was not solitary in its voyage through the inner solar system. What had initially seemed like a lone interstellar wanderer was now accompanied by faint, previously undetected companions, appearing almost simultaneously in multiple observations. The initial data suggested that these additional objects were not the result of observational artifacts or errors. Repeated imaging confirmed their presence. They shimmered like delicate sparks against the dark backdrop of space, each moving along trajectories that suggested subtle coherence with the original path of 3I Atlas, yet each also seemed to possess a degree of autonomy that defied simple classification. The discovery of this multiplicity transformed what had been a remarkable observation into a profound cosmic puzzle. Observers and theorists alike were compelled to reconsider the nature of interstellar travelers. Past examples, such as Oumuamua in 2017 and Comet Borisov in 2019, had been solitary phenomena, fleeting visitors that could be described and contextualized with a relative ease. A single object entering our solar system was already rare, and yet the emergence of multiple companions suggested a mechanism more complex than any previously witnessed. It was as if a single note had multiplied into a chorus, creating a symphony whose underlying structure was elusive, composed in a language that human science had only begun to interpret. The multiplicity challenged assumptions. Could these be fragments of a parent body shattered in some distant stellar event? Or was this cluster evidence of a previously unknown process of interstellar object formation? Early hypotheses quickly surfaced in scientific circles. One suggestion considered the possibility that 3I Atlas had originated from a distant, disintegrating exoplanetary system, where gravitational perturbations had liberated a small cloud of material, sending it drifting toward our Sunday. Another hypothesis speculated about tidal disruption events, in which a massive star or black hole might have fragmented a body, propelling the pieces across interstellar distances. Each explanation carried merit, but also revealed profound gaps. None could fully account for the observed consistency and coherence in the multiplication, nor the hyperbolic, high-velocity trajectories that resisted simple gravitational modeling. The objects appeared neither chaotic nor purely random. They exhibited patterns that implied some hidden order or process, an order that remained inaccessible to current observation techniques. Technological advancements allowed astronomers to refine their observations. High-resolution imaging from both ground-based observatories and space telescopes revealed subtle variations in brightness and composition among the companions. Some objects reflected light in ways suggesting unusual surface properties, while others hinted at the presence of volatile compounds that sublimated in the sparse sunlight of the inner solar system. The subtle spectral differences indicated a diversity that made a singular origin hypothesis more difficult to sustain. Were these variations a result of fragmentation and subsequent surface alteration, or did they reflect an intrinsic heterogeneity from the moment of formation, perhaps pointing to complex processes occurring far beyond the boundaries of the solar system? Moreover, the spatial arrangement of the objects introduced another layer of intrigue. The companions were not scattered indiscriminately. Their positions suggested a faint alignment, a pattern emerging over astronomical scales. The observed distribution appeared almost choreographed, hinting at subtle forces at work, whether gravitational interactions, radiation pressure effects, or influences yet to be identified. Such structure, however tenuous, demanded attention. The universe was presenting a tableau that simultaneously adhered to the rules of physics and yet subtly defied them, a duality that would fuel both rigorous investigation and speculative contemplation. International collaboration intensified in response. Observatories from multiple hemispheres coordinated tracking schedules, ensuring continuous coverage as the objects traversed the sky. Data sharing became critical. The slightest observational gap risked losing track of the faint companions, whose apparent velocities demanded high-frequency imaging and rapid analysis. Astronomers developed specialized software to identify and catalog the multiple objects, cross-referencing observations to refine orbital parameters and assess potential interactions. Each iteration revealed the astonishing complexity of the system, not merely a single hyperbolic visitor, but a dynamically evolving ensemble that challenged conventional assumptions about interstellar debris and small body dynamics. The realization of multiplicity also prompted reconsideration of the potential origins of 3I Atlas. Could this be a remnant of a disrupted exoplanetary system, a stream of debris ejected by gravitational interactions with a distant star? Or perhaps a fragment of a previously unknown class of interstellar phenomena, a cloud of small objects traveling collectively across the void? Each scenario carried profound implications. If the objects were remnants of a distant planetary system, we were witnessing material shaped by unknown cosmic events and processes, offering an unprecedented glimpse into the architecture of a far-off stellar neighborhood. Alternatively, if the multiplicity reflected an unknown interstellar mechanism, we were confronting evidence of processes entirely beyond the scope of terrestrial experience, a challenge to existing models of celestial mechanics and formation theory. The psychological impact on the scientific community should not be underestimated. Observing the gradual multiplication of objects evoked a mixture of fascination and unease. The notion that the solar system, usually so well charted, could be approached by multiple interstellar travelers, moving in patterns that partially adhered to known physics yet partially eluded explanation, forced a recalibration of expectation. Discussions in professional forums and correspondence were imbued with a tone of cautious wonder, as scientists attempted to reconcile empirical data with theoretical frameworks. Even as instruments confirmed the phenomenon, the human mind strained to comprehend a process so far removed from everyday experience, operating across distances and timescales that dwarfed terrestrial intuition. Simultaneously, public interest grew as the observations were shared through press releases and scientific briefings. Images of faint, multiplying points of light near Mars captured the imagination, evoking both awe and subtle unease. Philosophers and science communicators began reflecting on the broader implications. The universe, it seemed, was far from static, far from the predictable machine once envisioned. The multiplication of objects near our neighboring planet suggested that interstellar space was not merely a corridor of occasional passage, but a dynamic medium capable of delivering surprises, of challenging assumptions, and of provoking reflection on humanity's place in the cosmos. At the core of this discovery phase, a profound tension persisted between observation and understanding. Each new data point added clarity but also revealed deeper questions. The companions' hyperbolic orbits, their subtle alignment, their multiplicity, and their spectral diversity collectively suggested a phenomenon that was coherent yet resistant to complete explanation. The objects became symbols of both the triumph and the limits of human inquiry, a testament to observational rigor, collaboration, and technological advancement, but also a reminder that the universe operates with an autonomy that defies complete mastery. By the end of this phase, the scientific narrative had solidified around a single compelling theme. 3I Atlas was not alone, and its multiplication represented an extraordinary anomaly demanding further study. The initial surprise had evolved into a structured awareness of complexity, and while hypotheses proliferated, certainty remained elusive. The stage was set for deeper investigation, for the application of increasingly sophisticated instruments and analytical methods, and for the engagement of the broader scientific imagination. Humanity had glimpsed a dynamic, multiplying interstellar phenomenon, and the implications extended far beyond orbital charts and spectrographs, touching on the very nature of cosmic unpredictability and the fragile boundaries of knowledge. To contextualize the phenomenon of 3I Atlas and its multiplying companions, scientists turned to history, seeking analogues in the catalogue of interstellar visitors. The most immediate comparisons were to the two interstellar objects that had preceded it in modern observation, Oumuamua in 2017 and Comet Borisov in 2019. Both had arrived unannounced, solitary travelers from distant star systems, moving along hyperbolic trajectories that confirmed their interstellar origin. Yet, despite their singular nature, neither exhibited multiplicity. They were lone emissaries, their brief sojourns documented meticulously but limited in scope. In contrast, 3I Atlas approached Mars, not as a solitary wanderer, but as the leading element of a swarm, accompanied by faint but detectable companions whose synchronized motion suggested a coherence beyond random chance. The comparison illuminated the unprecedented nature of the current observation, a multiplicity of interstellar objects traveling collectively, a phenomenon without clear precedent. The historical perspective provided both reassurance and tension. On one hand, the observation of Oumuamua and Borisov demonstrated that interstellar objects could indeed traverse our solar system undetected until they were near enough to be captured by telescopic surveys. This suggested that 3A Atlas was part of a broader category of phenomena, existing within the known but rarely observed behavior of the cosmos. On the other hand, the multiplication challenged the very framework established by prior observations. The solar system had seen interstellar visitors before, but never in such numbers, never with companions appearing almost simultaneously. The pattern of movement, the hyperbolic trajectories, and the emergence of additional objects all implied mechanisms that extended beyond the scope of conventional interstellar dynamics. Historical catalogues were revisited in an attempt to identify overlooked anomalies. Astronomers sifted through decades of observation logs, scanning for instances of faint objects near interstellar visitors that might have gone unnoticed. Archival images from sky surveys revealed occasional faint companions in isolated cases, but none exhibited the clear multiplication observed with 3I Atlas. Even the closest analogues were faint and ambiguous, often attributable to observational artifacts, background stars, or instrumental noise. The multiplicity of 3I Atlas thus emerged not merely as a novel observation, but as a defining characteristic, a phenomenon distinct from anything previously documented. Past interstellar objects had already reshaped understanding, prompting refinements in detection techniques, orbit prediction, and compositional analysis. Oumuamua's unusual shape, its non-gravitational acceleration, and its enigmatic reflective properties had challenged assumptions about small body physics. Borisov, a more conventional comet, had nonetheless expanded the known chemical diversity of interstellar visitors. Against this backdrop, the multiplicity of 3I Atlas magnified the conceptual challenge. It demanded not only observational rigor, but theoretical flexibility, inviting astronomers to explore processes that could produce clusters of objects traveling through interstellar space in coordination. Historical comparison, while informative, offered no definitive answers. It highlighted both the continuity of cosmic phenomena and the emergence of something wholly unprecedented. The historical analogy also underscored the rarity of interstellar encounters. Despite centuries of astronomical observation, the number of confirmed interstellar objects remains vanishingly small. Each arrival is a fleeting window into the dynamics of distant star systems, a transient glimpse of materials shaped in environments fundamentally different from our own. In this context, the multiplication of 3I Atlas and its companions was not simply unusual, it was extraordinary. The phenomenon provided a natural laboratory for understanding interstellar processes, for testing models of small body dynamics, and for probing the limits of gravitational, radiative, and material interactions on cosmic scales. Yet it also reminded observers that the universe retains the capacity for surprise, that even well-established patterns can be punctuated by events that defy expectation. The historical perspective illuminated another subtle yet profound question: the nature of detection itself. Both Oumuamua and Borisov had been observed only because their paths intersected the regions actively monitored by modern telescopes. The apparent multiplicity of 3I Atlas raised the possibility that clusters of interstellar objects might be more common than previously assumed, their detection merely a matter of technological capability and observational serendipity. If interstellar clouds of small bodies occasionally traverse our solar system, unseen until they enter the inner regions, then humanity's catalogue of such phenomena represents only a fraction of the underlying reality. The historical comparison thus expanded the conceptual framework, inviting consideration of population statistics, observational bias, and the hidden dynamics of interstellar space. Historical context also provided a lens for philosophical reflection. Each interstellar object, whether solitary or multiplied, is a messenger from the vast reaches of space, a fragment of processes and environments far beyond Earth's immediate experience. Observing them evokes both humility and wonder, a recognition of the universe's scale and our limited perspective. By situating 3I Atlas alongside its predecessors, scientists and observers alike could appreciate the broader narrative. The solar system is not an isolated island, but a region through which objects from distant stars occasionally wander, bringing with them the imprint of unknown histories, dynamics, and material compositions. The multiplicity of the current phenomenon intensifies this reflection, reminding humanity that the cosmos operates according to patterns that may be subtle, complex, and often imperceptible until attention is focused with the precision of modern instrumentation. Furthermore, the historical comparison illuminated methodological lessons. The analysis of Oumuamua and Borisov had required rapid mobilization of observational resources, collaboration across institutions, and the development of flexible models to account for unexpected behavior. These lessons were immediately applied to 3I Atlas. Data sharing protocols were refined, tracking algorithms adjusted to account for multiple moving objects, and spectroscopic campaigns intensified to capture compositional diversity. Historical analogues thus provided both conceptual context and practical guidance, demonstrating how previous encounters could inform contemporary analysis while simultaneously highlighting the limitations imposed by novelty. Finally, the historical perspective emphasized the intersection of expectation and surprise. In prior interstellar encounters, scientists were prepared to witness rare events but were not equipped for complexity on this scale. Multiplicity introduced a new dimension of unpredictability, a challenge that could not be fully anticipated from past experience. The juxtaposition of familiarity and novelty, the recognition of 3I Atlas as an interstellar object alongside the unprecedented observation of companions, created a tension that drove both curiosity and cautious speculation. This tension, informed by history yet unbounded by it, formed the foundation for the next phase of investigation, a careful, systematic examination of the scientific shock, the anomalies, and the questions that would define the evolving narrative of 3I Atlas as it approached Mars and continued its journey through the solar system. The revelation that 3I Atlas was multiplying near Mars sent shockwaves through the astronomical community. While the discovery itself was remarkable, the implications of multiplicity challenged assumptions about interstellar dynamics and small-body physics. Scientists began to confront a level of strangeness that blurred the line between observable phenomenon and theoretical anomaly. To understand the depth of this shock, it is necessary to examine both the empirical data and the conceptual frameworks that were unsettled by these observations. At the heart of the scientific astonishment was the realization that conventional models of celestial mechanics offered no straightforward explanation. Single interstellar objects, though rare, had been incorporated into orbital simulations with predictable parameters. Hyperbolic trajectories governed primarily by the Sun's gravity, minor perturbations from planetary bodies, and interactions with solar radiation pressure. Multiplicity, however, introduced complexities that defied these models. Each new companion altered the collective gravitational environment in subtle ways. When plotted, their trajectories appeared neither entirely independent nor rigidly linked, suggesting the presence of forces or historical interactions beyond the immediate detection capabilities of modern instruments. These anomalies forced theorists to reconsider the applicability of standard N-body simulations and to explore alternative explanations that could account for the observed behavior. Adding to the difficulty was the apparent coherence among the companions. Unlike random fragments scattered by explosive or disruptive events, the objects near 3I Atlas maintained relative positional consistency over weeks of observation. Their hyperbolic velocities were similar, yet not identical, revealing a pattern of subtle deviations that hinted at unseen influences. The question arose: were these objects remnants of a single parent body, broken apart by distant gravitational interactions or collisions, or were they independently formed entities, somehow synchronized by the vast dynamics of interstellar space? Each hypothesis carried profound implications, yet none offered a completely satisfactory explanation. The situation illustrated a fundamental principle of scientific shock. When observed phenomena violate expectations, the shock is not merely emotional, but deeply conceptual, revealing the limitations of existing models and prompting the creation of new theoretical frameworks. The uniqueness of the event became more apparent when contrasted with known cometary or asteroid clusters within the solar system. Within our planetary neighborhood, clusters of small bodies, whether in asteroid families, Kuiper belt objects, or cometary fragments, arise through well-understood mechanisms, collisions, tidal disruptions, or gravitational resonances. However, these processes are anchored to the dynamics of the solar system itself. Interstellar objects, by definition, arrive from beyond these boundaries, moving through gravitational fields with vastly different histories. The multiplication observed with 3I Atlas suggested either a previously unrecognized interstellar mechanism or a set of rare circumstances producing clustering at vast distances prior to arrival in our system. Both possibilities carried a profound sense of scientific surprise. The shock was compounded by preliminary analyses of acceleration. Early data suggested that some companions exhibited slight, non-gravitational accelerations, reminiscent of the anomalous behavior observed with Oumuamua. In that case, subtle changes in velocity were attributed to outgassing or radiation pressure, yet even these explanations remain debated. For 3I Atlas, the multiplicity complicated the interpretation. Were the accelerations the result of asymmetric forces acting on individual objects, or did they reflect collective interactions, perhaps mediated by radiation or unknown interstellar processes? These questions intensified the sense of bewilderment. The multiplying bodies were not only unexpected in number, but also unpredictable in motion. Professional discussions captured the spectrum of scientific reactions. Some astronomers described the scenario as intriguing but perplexing, highlighting the combination of measurable behavior and unexplained anomalies. Others framed it in more stark terms, a challenge to the assumptions that underpin interstellar small body theory. potentially indicating processes or phenomena that had gone unnoticed for millennia. The debate was both technical and philosophical. It was not merely about cataloguing objects, but about grappling with the realization that our frameworks for understanding cosmic mechanics were incomplete. The shock was therefore multidimensional, operating simultaneously at the empirical, theoretical, and existential levels. In addition, the phenomenon sparked reflection on the limits of observational certainty. Even with the most precise instruments, faint objects in the vastness of space can reveal only partial information. Measurements of velocity, trajectory, brightness, and composition are constrained by instrumental sensitivity, atmospheric interference, and temporal coverage. When the observed objects defy expectations, these constraints become more pronounced. Scientists faced the delicate task of distinguishing genuine anomalies from observational artifacts, all while acknowledging the possibility that the universe was presenting events inherently outside our predictive capacities. The shock, therefore, was both epistemological and empirical. It challenged what we know, how we know it, and the confidence with which we model the cosmos. The emotional resonance of scientific shock should not be underestimated. Beyond the technical details, there is a human dimension to witnessing phenomena that defy understanding. Astronomers describe a blend of excitement and unease, exhilaration at observing something extraordinary, tempered by the realization that conventional understanding provides no ready explanation. The multiplying 3I Atlas objects became symbols of the cosmos's capacity for surprise, of the thin boundary between observation and comprehension. For the broader public, the notion that interstellar objects could arrive not in isolation but as a subtle swarm introduced a poetic tension. The universe was at once knowable and profoundly mysterious, offering glimpses of order while withholding the full narrative. The shock also emphasized the necessity of open-minded speculation. While empirical rigor remained paramount, the unexplained multiplicity invited theoretical exploration. Could dark matter interactions influence small body trajectories over interstellar distances? Might unknown electromagnetic forces play a subtle role? Were these bodies remnants of exotic astrophysical events, fragments of distant supernovae or planetary disruptions? While speculative, these considerations were grounded in the recognition that when nature presents anomalies, expanding conceptual frameworks is essential to progress. The shock of 3I Atlas was therefore both a challenge and an opportunity, a call to extend physics beyond familiar boundaries, to confront the limits of modeling, and to embrace uncertainty as a driving force for inquiry. Ultimately, the scientific shock of 3I Atlas, multiplied near Mars, exemplifies the tension between expectation and observation. It reminds us that the universe, vast and indifferent, is capable of producing events that simultaneously adhere to physical law and resist comprehension. The multiplying companions are not merely catalogued points of light, they are provocations, inviting reflection on the scope and limitations of human understanding. They challenge assumptions, provoke hypotheses, and, most profoundly, illuminate the intersection of empirical rigor with the sublime, the awe that arises when the cosmos gestures beyond the familiar, revealing patterns that are both inscrutable and mesmerizing. In the days following the confirmation of multiplicity, the shockwaves rippled through the scientific literature and conference halls. Researchers began preparing papers, proposing models, and recalibrating observational strategies. The event had transformed from an isolated observation into a defining moment for the study of interstellar objects, raising questions that would guide inquiry for years to come. Yet, even amid the data, graphs, and simulations, the emotional core remained, a recognition of humanity's encounter with the unexpected, a subtle but undeniable tremor in the fabric of understanding, as the universe revealed, in faint multiplying points of light, that it retains mysteries vast, intricate, and unyielding. The multiplying companions of 3I Atlas presented astronomers with a labyrinth of orbital peculiarities. Each trajectory, a puzzle that resisted immediate interpretation. Unlike typical asteroids or comets within our solar system, which follow elliptical orbits shaped primarily by the Sun's gravity and modulated by interactions with planets, these objects moved along hyperbolic paths. Each object's velocity exceeded the escape velocity of the Sun at its location, confirming its interstellar origin. Yet the subtle variations among companions were profound. Some accelerated slightly more than others, their paths diverging in minute but measurable ways. This divergence suggested influences beyond simple gravitational mechanics, challenging the predictive power of classical orbital models and introducing a profound sense of uncertainty. Mapping these trajectories required meticulous analysis. Observatories worldwide coordinated to ensure continuous tracking, combining optical imaging, radar observations, and astrometric measurements. Each data point was critical, as even small errors could propagate into significant miscalculations over the vast distances involved. The resulting orbital plots were both elegant and confounding, a cluster of points tracing sweeping, hyperbolic arcs that intersected near Mars, yet retained distinct individuality. The arrangement hinted at forces acting over long timescales and distances, possibly stemming from interactions in the interstellar medium, subtle radiation pressure effects, or perturbations from unknown masses. Yet no single mechanism fully accounted for the observed complexity, leaving astronomers both awed and frustrated by the delicate interplay of apparent order and inexplicable deviation. One of the most striking aspects of the orbital data was the degree of coherence among the objects. Despite individual deviations, there was a faint but discernible alignment along a common vector of approach toward the inner solar system. This alignment raised questions about their formation and history. Were these fragments of a once cohesive parent body, disrupted perhaps in a distant gravitational encounter or a tidal event near a massive star? Or did they emerge independently, their paths coincidentally converging in a manner that produced a coherent but perplexing pattern? Each possibility carried profound implications for understanding interstellar object dynamics and hinted at processes operating far beyond current observational reach. The anomalies extended beyond mere positioning. Subtle changes in velocity, inconsistent with gravitational acceleration alone, suggested additional forces at play. In some cases, small but measurable deviations could potentially be attributed to radiation pressure photons exerting force on irregular surfaces, producing minute accelerations over time. However, the variations did not uniformly correspond to expectations from surface reflectivity or size estimates, implying either unknown compositional properties or additional environmental influences. Some scientists speculated that interactions with the interstellar medium, though sparse, might produce drag effects sufficient to slightly alter trajectories over millions of kilometers. Yet these explanations remained tentative, reinforcing the sense that the observed orbital behavior was genuinely anomalous. The hyperbolic velocities of these objects were themselves extraordinary. Measurements indicated speeds exceeding tens of kilometers per second relative to the Sun, consistent with expectations for interstellar origin, but remarkable when considered alongside multiplicity. Coordinating velocities among multiple objects suggested a shared history, perhaps indicative of ejection from a common system. Yet no known mechanisms could simultaneously account for the observed spread of velocities, the apparent coherence in approach, and the subtle divergences among companions. The orbital data thus became a focal point for both excitement and intellectual tension. The mathematics described something real, but it also described something that defied existing explanatory frameworks. Interactions with planetary gravities introduced additional complexity. As 3I Atlas approached the vicinity of Mars, scientists modeled potential perturbations from the planet's mass. While the overall influence on hyperbolic trajectories was minor, the small deflections offered a natural experiment in gravitational interaction. Observing how these objects responded to planetary fields provided critical data for understanding their mass, composition, and potential non-gravitational forces. Yet even after accounting for these influences, residual deviations persisted, highlighting the inadequacy of current models to fully capture the nuances of interstellar swarm dynamics. These orbital oddities had significant implications for scientific methodology. Traditional simulations of interstellar object motion, which treated single objects in isolation, were insufficient. Researchers had to incorporate multi-body dynamics, radiation pressure models, and potential interstellar medium interactions. Computational models grew increasingly sophisticated, yet even the most advanced simulations failed to fully replicate the observed paths. This discrepancy underscored the dual nature of the shock, empirical certainty in measurements coexisting with theoretical uncertainty in interpretation. The universe was presenting data that were real, precise, and replicable, yet resistant to classical explanation. The sense of wonder was compounded by the visual elegance of these trajectories. When plotted in three-dimensional space, the companions traced delicate arcs, converging near Mars and then diverging again, their motions reminiscent of dancers performing a silent choreography across the void. The aesthetic beauty of the orbits amplified the philosophical resonance of the observation. Here was a cosmic pattern, elegant and mysterious, defying immediate understanding, yet evocative of order and intentionality. Observers, both scientific and contemplative, could not help but reflect on the interplay between apparent randomness and underlying structure, a theme resonant across both physics and philosophy. Another intriguing element was the temporal aspect of motion. Each companion arrived with slightly different timing, their approach staggered over days and weeks. This temporal distribution complicated detection, requiring continuous monitoring to ensure that the faintest objects were not lost. It also suggested a history of interaction. Perhaps the objects had experienced differential acceleration in interstellar space, or perhaps fragmentation events occurred over extended intervals, producing the observed spread in arrival times. Each hypothesis carried explanatory power, but also new questions, reinforcing the depth and complexity of the mystery. The orbital oddities of 3I Atlas and its companions ultimately crystallized the tension between knowledge and uncertainty. On one hand, precise measurements confirmed the existence, motion, and hyperbolic nature of the objects. On the other, the behavior of the swarm defied simple physical explanation, hinting at processes, histories, or forces beyond immediate comprehension. This duality encapsulated the essence of scientific wonder, the recognition that empirical observation, while foundational, can simultaneously illuminate and mystify, drawing the observer deeper into a landscape where known laws interact with phenomena that stretch imagination and theory alike. As data continued to accumulate, astronomers refined models, adjusted simulations, and proposed hypotheses to account for the observed anomalies. Each iteration brought incremental understanding, yet the core strangeness persisted. Multiple interstellar objects, moving coherently yet unpredictably, approaching Mars along hyperbolic trajectories. The orbital oddities, measured with ever-increasing precision, became both a tool and a symbol, a means to probe the dynamics of the cosmos and a reminder of the limits of human comprehension. In these subtle deviations, the universe revealed its capacity for both pattern and enigma, presenting a challenge that was as philosophical as it was scientific, and setting the stage for deeper investigation into the composition, interactions, and ultimate origins of this interstellar swarm. The subtle complexities of 3I Atlas and its companions demanded not only theoretical insight, but also the full power of observational technology. Tracking multiple faint objects traveling at hyperbolic velocities required instruments capable of detecting minute variations in position, brightness, and spectral characteristics across immense distances. In the early days of discovery, astronomers relied heavily on a network of ground-based telescopes distributed across the globe, from the high-altitude observatories of Mauna Kea to the expansive arrays in the Chilean Andes. These instruments provided the necessary spatial coverage to maintain continuous observation, ensuring that no companion would be lost in the vast darkness of space. Each observatory contributed incremental data points, feeding into a collective system designed to triangulate positions with exquisite precision. Among the key instruments was the Pan-STARRS telescope in Hawaii, whose wide-field survey capabilities allowed it to detect faint, transient objects across the night sky. This facility had first recorded 3I Atlas, capturing the initial hyperbolic trajectory and providing baseline data for subsequent analysis. As the multiplicity of companions became apparent, Pan-STARRS was complemented by the Las Cumbres Observatory Global Network, a series of robotic telescopes strategically positioned to provide round-the-clock monitoring. Observers coordinated scheduling to ensure near-continuous coverage, mitigating the gaps that could obscure faint objects as they traversed the sky. Each new observation refined orbital parameters, confirming that the companions were not random background objects, but components of a coherent, if enigmatic, system. High-resolution imaging from space-based observatories added another layer of insight. The Hubble Space Telescope, despite its original mission focus on distant galaxies and nebulae, was repurposed to capture faint companions with unparalleled clarity. Its instruments provided detailed measurements of brightness variations, enabling astronomers to infer size, shape, and rotation rates. Subtle fluctuations in reflected light revealed potential asymmetries on object surfaces, while photometric data suggested compositional heterogeneity. This information was crucial. Variations in albedo and reflectivity could influence non-gravitational accelerations, offering potential explanations for minor deviations observed in orbital trajectories. Hubble's observations, combined with the continuous ground-based monitoring, allowed the construction of a more complete three-dimensional map of the swarm's movement through the inner solar system. Radar observations, though limited by distance and object size, provided additional verification of position and velocity. Facilities such as the Goldstone Deep Space Communications Complex were employed to transmit radio waves toward the objects, measuring reflections to estimate distance and radial motion. These measurements confirmed hyperbolic velocities and provided independent corroboration of optical tracking. For the faintest companions, radar was challenging, but still offered critical constraints on motion and orientation. The integration of optical, photometric, and radar data created a multifaceted observational framework, enabling scientists to cross-check findings and reduce uncertainty. Astrometry, the precise measurement of positions and movements, became the backbone of the tracking effort. Sophisticated software pipelines were developed to process vast quantities of data, identify faint objects, and differentiate genuine companions from background stars or imaging artifacts. These computational tools relied on pattern recognition, orbital fitting algorithms, and statistical modeling to isolate true interstellar objects. The software incorporated feedback loops. Each new observation refined the predicted positions, which in turn guided telescope scheduling for subsequent nights. This iterative approach ensured that even the faintest companions remained under continuous surveillance, their trajectories mapped with precision that would have been impossible a few decades earlier. Spectroscopy added another critical dimension, revealing the chemical fingerprints of the object's surfaces. Instruments such as the Very Large Telescope's X-shooter and the Keck Observatory's DMOS spectrographs measured reflected light across multiple wavelengths, capturing absorption lines indicative of mineralogical and molecular composition. Early data suggested a diversity among companions. Some showed spectral signatures consistent with silicate-rich material, while others hinted at ices and volatile compounds. This diversity complicated origin hypotheses. If all objects were fragments of a single parent body, one might expect compositional homogeneity. The observed heterogeneity implied either post-ejection surface evolution or a more complex formative environment, possibly within a protoplanetary or circumstellar debris field. Infrared observations complemented optical and spectroscopic data, probing thermal emissions to estimate size and surface properties. The Spitzer Space Telescope, in its final operational phases, contributed valuable infrared measurements, enabling scientists to infer approximate diameters and albedos of the faint companions. These measurements, combined with optical photometry, allowed more accurate calculations of mass and density, parameters essential for modeling non-gravitational influences such as outgassing or radiation pressure. Each layer of observational data refined the collective understanding of the swarm, transforming vague dots of light into quantifiable entities with distinct physical characteristics. The orchestration of these diverse instruments exemplified the interdisciplinary collaboration at the heart of modern astronomy. Optical, radar, spectroscopic, and infrared observations converged to produce a multidimensional portrait of 3I Atlas and its companions. Data pipelines integrated streams from observatories separated by thousands of kilometers, harmonizing temporal and spatial resolutions to construct coherent models of motion and composition. The technological achievement was matched by the human effort required. Astronomers meticulously coordinated observation schedules, validated measurements, and cross-checked computational models, creating a living, dynamic framework for understanding a phenomenon that defied prior experience. Yet even with this arsenal of instruments, questions persisted. Non-gravitational accelerations remained difficult to reconcile with measured sizes and estimated compositions. Subtle divergences in velocity hinted at influences beyond direct observation, possibly arising from interstellar medium interactions or unknown forces. The multiplicity of the swarm challenged assumptions about coherence and origin, while variations in spectral characteristics suggested a complex history of formation and evolution. The instruments had revealed the phenomenon in exquisite detail, yet they had also illuminated the depth of mystery, confirming that the observed behavior of 3I Atlas and its companions was not merely unusual but fundamentally puzzling. In this environment, each telescope, detector, and software pipeline became an instrument of discovery, extending human perception into the remote reaches of space. Observations were no longer passive recordings. They were active engagements with a system that responded subtly to forces, time, and distance. Every data point was both evidence and question, offering insight while prompting new lines of inquiry. The swarm of 3I Atlas companions, once faint points of light, had become a laboratory of interstellar dynamics, a canvas upon which the universe displayed both predictable law and inscrutable mystery. Through this technological lens, the phenomenon began to take shape as a multidimensional puzzle. Trajectories were plotted with increasing confidence, compositions characterized with nuanced precision, and non-gravitational forces measured against rigorous standards. Yet for all this clarity, the deeper questions, the origin of multiplicity, the coherence of motion, the subtle accelerations remained unresolved. In the interplay of observation and anomaly, the scientific method itself was tested, demonstrating both its power to reveal and its humility in the face of the unknown. Each instrument, from telescope to spectrograph, became a bridge between human understanding and cosmic reality, translating faint photons into knowledge while simultaneously exposing the limits of that knowledge. The deployment and integration of these observational tools exemplify the extraordinary lengths to which science must go when confronting phenomena that push the boundaries of prior experience. 3. Atlas and its companions demanded coordination, precision, and creativity, drawing upon decades of technological advancement. Yet even amid this technological triumph, the sense of wonder persisted. The objects moved silently through the void, indifferent to human scrutiny, yet their faint signals carried a message of mystery. The cosmos is vast, dynamic, and full of surprises, and the act of observation is simultaneously a means of discovery and a reminder of the universe's inscrutable nature. As telescopes and instruments mapped the trajectories of 3I, Atlas and its companions, attention turned to the spectral signatures of these enigmatic objects. Spectroscopy, the study of light as it interacts with matter, offers an unparalleled glimpse into composition, revealing the mineral and molecular constituents of distant celestial bodies. For interstellar objects, which cannot be physically sampled, spectra provide the most direct connection between observation and the physical reality of the bodies themselves. In the case of 3I Atlas, the spectral data revealed a richness and complexity that deepened both fascination and mystery. Initial observations focused on reflected sunlight across the visible spectrum. Photometric analysis indicated variability in brightness among the companions, suggesting differences in size, shape, or surface composition. Some objects exhibited consistent albedo, reflecting a steady fraction of incident light, whereas others fluctuated subtly, hinting at irregular surfaces or rotation. These variations, when plotted over time, allowed astronomers to estimate rotation periods, detect tumbling motions, and infer shapes ranging from elongated fragments to more spherical bodies. Such diversity indicated that these were not uniform fragments produced by a single mechanical disruption, but potentially objects shaped by distinct formative processes or environments. Spectral measurements extended into the near-infrared, capturing absorption bands associated with silicates, ices, and organic compounds. Several companions displayed strong features consistent with silicate minerals, reminiscent of rocky bodies within the solar system, while others showed signatures suggesting frozen volatiles, water, carbon monoxide, or ammonia, more typical of comets. The presence of these compounds at interstellar distances implied preservation over immense timescales, a testament to the cold, stable conditions of the object's origin. Yet, the diversity also complicated origin theories. If all companions were fragments of a single parent body, compositional homogeneity might be expected. The observed heterogeneity suggested either a complex parent object with differentiated layers or a collection of independently formed bodies that converged in trajectory. Beyond composition, the spectral data revealed subtle anomalies. Some objects reflected light in a manner inconsistent with standard modeling, exhibiting slightly higher reflectivity at certain wavelengths. These anomalies raised questions about surface texture, porosity, or the presence of materials uncommon in known solar system bodies. Could these surfaces contain exotic silicates, unusual ices, or even compounds altered by long exposure to interstellar radiation. Each possibility introduced new dimensions to the mystery, linking chemical composition with dynamical behavior and suggesting that the companions' histories extended far beyond the reach of current observation. Temporal variation in spectra provided further insight. Repeated observations indicated minor fluctuations in absorption features, hinting at sublimation or surface alteration as the objects moved closer to the sundial. Such behavior is reminiscent of comets, which release gas and dust when heated, creating faint outgassing that can subtly alter trajectory. For 3I Atlas companions, the spectral signatures suggested minimal but detectable activity, sufficient to explain small, non-gravitational accelerations observed in orbital data. This reinforced the notion that interstellar objects are not inert. They interact with radiation and solar wind in subtle ways, revealing dynamic behavior despite the vast distances from their origin systems. The spectra also provided clues about potential ages and histories. The preservation of volatile compounds suggested that these objects had remained in cold interstellar space for millions of years, avoiding collisions and thermal alteration. Simultaneously, differences among companions implied varied thermal histories or exposure to differing cosmic environments prior to arrival. One could imagine fragments wandering the galaxy, shaped by the gravitational fields of passing stars, buffeted by cosmic rays, and occasionally heated by nearby stellar encounters, until their converging trajectories brought them to the solar system. In this sense, spectral data offered not just a chemical fingerprint, but a narrative of cosmic travel, encoding the story of a long journey across the void. Comparisons to known interstellar objects added perspective. Oumuamua had exhibited unusual reflective properties, while Borisov had shown typical cometary ice composition. 3I Atlas, by contrast, displayed both diversity and multiplicity, a combination that suggested either an extraordinarily complex parent system or an entirely new class of interstellar phenomena. Spectroscopy, while illuminating, reinforced the sense of strangeness. These were objects familiar in some respects, composed of rock and ice, yet arranged and behaving in ways entirely novel to human observation. The multiplicity, coupled with spectral heterogeneity, challenged existing taxonomies of small body classification, prompting astronomers to consider broader frameworks that could accommodate unprecedented variability. The spectral observations also intersected with broader astrophysical questions. What can the composition of these objects tell us about distant star systems? Do their chemical signatures reflect standard processes of planetary formation, or do they hint at exotic mechanisms unique to their birth environment? Each absorption line, each subtle shift in wavelength, became a data point for reconstructing histories that occurred light years away. By studying the companions collectively, astronomers hoped to discern patterns suggestive of formation within a protoplanetary disk, a disrupted planetary system, or even more exotic contexts such as tidal disruption near a massive star. Spectroscopy thus functioned as both diagnostic tool and narrative medium, linking chemical fingerprints with cosmic stories. The observational challenges were immense. The objects were faint, often barely distinguishable from background stars. Instrumental sensitivity, atmospheric interference, and temporal coverage constrained data collection. To mitigate these limitations, astronomers combined observations from multiple instruments, averaging spectra, cross-validating absorption features, and employing statistical models to enhance signal detection. The resulting composite spectra revealed robust patterns, but also subtle discrepancies that demanded caution in interpretation. Even with sophisticated methods, the universe retained its capacity for ambiguity, reminding observers that understanding often comes incrementally, through patient accumulation of evidence rather than sudden revelation. Finally, the spectral data underscored the interplay between observation and speculation. While measurements grounded the phenomenon in empirical reality, interpretation required theoretical creativity. Could the observed heterogeneity arise from differences in surface irradiation over millions of years, from cosmic ray processing, from partial fragmentation of a parent body with varied composition? Each scenario linked chemistry to physics, history to dynamics, and observation to imagination. The spectral signatures of 3I Atlas and its companions thus became both evidence and inspiration, proof of interstellar origin, and a canvas for contemplating the extraordinary complexity of the cosmos through the faint, shifting colors of light reflected across billions of kilometers. The study of 3I Atlas and its companions took a surprising turn when orbital analysis revealed subtle accelerations that could not be explained by gravity alone. Unlike the predictable paths of most small bodies, these objects displayed minute deviations, their velocities fluctuating slightly as they traversed interplanetary space. Such anomalies, though small in absolute terms, were statistically significant and consistent across multiple observations, prompting scientists to consider non-gravitational influences as plausible contributors. The phenomenon echoed earlier debates surrounding Oumuamua, whose unexpected acceleration had sparked speculation about cometary outgassing, radiation pressure, or even more exotic mechanisms. With multiple companions now exhibiting similar behaviors, the scale and complexity of the puzzle intensified. The non-gravitational accelerations were quantified by meticulously comparing observed positions against predicted paths generated by classical orbital mechanics. Small discrepancies, measured in meters per second, suggested the presence of forces acting on the objects in addition to solar gravity. For some companions, the accelerations aligned with models of anisotropic outgassing, where volatile compounds sublimated unevenly from irregular surfaces, producing gentle thrust. Yet, not all deviations conformed to this explanation. Several objects exhibited accelerations inconsistent with surface activity, raising the possibility of alternative influences such as radiation pressure from sunlight acting on low-mass, high-reflectivity surfaces. The magnitude and directionality of these accelerations required careful modeling. Scientists incorporated parameters, including object size, estimated mass, shape, albedo, and rotation. Even minor variations in these properties could produce measurable differences in motion over interplanetary distances. The process involved iterative simulations. Each companion was treated as a separate entity, with gravitational interactions among the group and with planetary bodies included. The results confirmed that while some acceleration could be attributed to conventional mechanisms, residual anomalies persisted, defying full explanation. These persistent deviations suggested that either current models were incomplete or that the objects possessed unusual physical properties not observed in familiar comets or asteroids. Observational data from multiple wavelengths complemented the orbital analysis. Infrared measurements, which provided estimates of size and thermal properties, were critical for assessing how radiation pressure might influence motion. Variations in reflectivity, surface composition, and rotational orientation were integrated into dynamic models to predict acceleration due to solar photons. For some companions, these calculations partially accounted for observed deviations, yet the alignment was never perfect. The persistent discrepancy implied the presence of either subtle, unmeasured forces or an intrinsic property of the objects themselves, such as low density, porous structures, or exotic surface materials. The idea of outgassing was explored in detail, inspired by the behavior of comets entering the inner solar system. Sublimation of volatile compounds produces reactive thrust, gradually altering trajectories in ways that can mimic accelerations not attributable to gravity alone. Spectroscopic observations revealed the presence of ices on several companions, suggesting that sublimation could indeed be a contributing factor. However, the faintness and small size of the objects made quantifying outgassing difficult, and for some companions, spectral data showed little evidence of active sublimation. This inconsistency reinforced the notion that multiple mechanisms might be at work, interacting in complex ways to produce the observed anomalies. Radiation pressure, the force exerted by photons impacting a surface, offered an additional explanatory avenue. For low-mass, highly reflective bodies, even the subtle momentum transfer from sunlight can produce detectable accelerations over astronomical distances. Models incorporating albedo, cross-sectional area, and orientation relative to the Sun suggested that radiation pressure could account for some observed deviations. Yet the magnitude of acceleration in certain companions exceeded predictions, implying either underestimated surface reflectivity, unusual geometry, or contributions from other forces. The persistence of anomalies across multiple objects hinted at systemic factors rather than random measurement error, reinforcing the sense of scientific intrigue. Gravitational interactions, though fundamental, could not fully resolve the mystery. Simulations including perturbations from planets, the Sun, and mutual interactions among companions provided a baseline for expected motion. Deviations beyond this baseline indicated forces acting independently of classical gravity. The precise measurement of hyperbolic trajectories allowed astronomers to isolate these anomalies, revealing that non-gravitational accelerations were consistent in direction relative to the Sun in some cases, and more complex in others. This nuanced pattern suggested that each object's motion was influenced by a combination of intrinsic properties, solar radiation, and potentially even interstellar environmental factors. The presence of multiple accelerating objects intensified theoretical speculation. If each companion exhibited independent, non-gravitational forces, then the phenomenon might represent a class of interstellar bodies with unusual structural or compositional characteristics. Porosity, surface roughness, and rotational dynamics could collectively produce subtle accelerations not commonly observed in typical comets or asteroids. Alternatively, the consistency of acceleration across multiple companions raised the possibility of coordinated environmental effects, such as interactions with sparse interstellar medium particles or magnetic fields. While these scenarios remained speculative, they underscored the need for interdisciplinary study, bridging astrophysics, materials science, and celestial mechanics. The non-gravitational acceleration had implications beyond trajectory prediction. It offered clues to the physical nature of the companions, informing estimates of mass, density, and surface properties. Even minor deviations could reveal internal structure, revealing whether the objects were solid fragments, loosely bound aggregates, or even highly porous composites shaped by millennia of interstellar travel. By integrating dynamical measurements with spectral and photometric data, astronomers began to construct a more holistic understanding of the swarm, transforming dots of light into dynamic entities with distinct, measurable characteristics. Importantly, these anomalies emphasized the philosophical dimensions of observation. Even in the face of precise measurement, the objects defied full comprehension, illustrating the tension between empirical certainty and theoretical uncertainty. The subtle accelerations were small enough to be measured, yet profound in implication. The universe was operating in ways that extended beyond conventional models, offering both insight and mystery. For scientists and observers alike, the phenomenon became a symbol of cosmic subtlety, a reminder that even faint points of light can harbor complexity far beyond expectation. As data continued to accumulate, the pattern of accelerations became increasingly clear. Some companions appeared influenced primarily by radiation or sublimation, while others resisted straightforward interpretation. The multiplicity of objects allowed comparative study, revealing both commonalities and deviations that suggested a spectrum of properties within the swarm. Each deviation prompted new hypotheses, from structural heterogeneity to exotic material composition, illustrating the iterative nature of scientific inquiry. Measurement led to modeling led to anomaly identification, and anomaly identification led to speculation that, in turn, guided further observation. Ultimately, the acceleration anomalies of 3I Atlas and its companions highlighted the intricate interplay of observation, theory, and uncertainty. They confirmed the reality of the phenomenon, provided insights into the physical properties of the objects, and simultaneously expanded the conceptual horizon of interstellar science. In these subtle motions, the universe communicated both data and mystery, revealing that even amidst rigor and precision, there remain behaviors that defy immediate explanation, compelling observers to continually refine models, expand imagination, and embrace the profound complexity of the cosmos. The emergence of multiple interstellar objects near Mars demanded an unprecedented level of collaboration among astronomers across the globe. No single observatory could maintain continuous surveillance of the faint, hyperbolic travelers. The sky's rotation and the object's rapid motion necessitated round-the-clock coverage. From the snow-covered peaks of Mauna Kea to the arid expanses of Chile's Atacama Desert, telescopes were coordinated in a meticulous choreography, each contributing slices of observational time that, when combined, formed a nearly continuous record of motion. This global network exemplified the human capacity to unite across geographies and disciplines, driven by curiosity and the urgent need to document a phenomenon defying prior experience. Data-sharing protocols became crucial in this international effort. Observatories uploaded measurements to centralized databases, where orbital parameters, photometric readings, and spectroscopic results were integrated in real time. Sophisticated software pipelines analyzed the influx of information, cross-referencing coordinates and brightness data to confirm the identity of individual companions. Given the faintness of these objects and the potential for background stars to masquerade as additional companions, rigorous verification was essential. Each new observation was scrutinized for consistency, ensuring that the swarm's apparent multiplication reflected reality and not instrumental artifacts. The human element remained vital, with astronomers manually inspecting images, comparing frames, and confirming detections before integrating them into predictive models. Collaboration extended beyond data management. Scientists specializing in orbital dynamics, spectral analysis, and thermal modeling worked in concert to interpret the incoming information. Computational astrophysicists ran simulations to test hypotheses about the swarm's origin and evolution, integrating gravitational influences, radiation pressure, and potential outgassing. Planetary scientists assessed interactions with Mars and the inner solar system, calculating the minimal but measurable perturbations that the planet's gravity might induce. Chemists and materials scientists examined spectral signatures to infer composition, porosity, and potential structural heterogeneity. The interplay of expertise illustrated the interdisciplinary nature of modern astronomy. A single discovery demanded the integration of knowledge from multiple fields, each lens refining the collective understanding of an extraordinary phenomenon. The coordination effort also required innovation in observational strategy. Given the object's faintness and hyperbolic velocities, astronomers employed adaptive scheduling, prioritizing telescopes based on predicted visibility windows. When one observatory experienced poor weather or technical limitations, others could adjust to compensate, creating a seamless observational chain. Robotic telescopes, programmed for rapid repositioning, proved particularly valuable in maintaining coverage. Real-time communication between teams allowed adjustments to imaging sequences, exposure times, and spectral scans, ensuring that each companion remained under continuous scrutiny. In essence, the swarm's motion dictated human activity on Earth, shaping telescope time, observation schedules, and data analysis priorities. Beyond observational logistics, the collaboration revealed the human side of discovery. Astronomers reported moments of shared awe, particularly when multiple companions appeared in a single frame, shimmering faintly against the void. Conferences and virtual meetings buzzed with excitement, tempered by caution. Every new data point required validation, every interpretation had to withstand peer scrutiny. Yet the collective sense of participating in a historical moment, observing a rare interstellar phenomenon unfolding in real time, imbued the work with an emotional resonance that transcended technical measurement. The multiplicity of 3I Atlas became a shared human experience as much as a scientific challenge. International collaboration also allowed for cross-validation of instruments and methodologies. Optical observations were compared with radar data to confirm distances and velocities. Spectroscopic readings from different facilities were calibrated against standard stars, ensuring consistency across the network. Each layer of verification enhanced confidence in the reality of the companions and their anomalous behavior, while simultaneously highlighting the subtle differences introduced by instrument sensitivity, atmospheric conditions, and observational geometry. This rigorous approach underscored the reliability of conclusions drawn from a phenomenon that, by its very nature, challenged expectations. In addition to professional collaboration, public communication became an essential dimension of the effort. Astronomers engaged with media, scientific organizations, and public outreach platforms to convey the significance of the observations while tempering sensationalism. Images of the faint swarm near Mars captured imaginations worldwide, prompting questions about the nature, origin, and potential implications of the objects. Communicating the complexity without distortion required careful phrasing, emphasizing empirical data, highlighting uncertainties, and conveying the sense of wonder and mystery inherent in interstellar exploration. This dialogue between scientists and the broader public reflected a modern understanding of discovery as both a technical and cultural event. The collaborative efforts revealed patterns in the swarm's behavior that might have gone unnoticed in isolated observation. By comparing simultaneous data from multiple locations, astronomers identified subtle alignments, variations in velocity, and changes in brightness across companions. These comparative analyses allowed for refinement of orbital models and improved predictions for future positions. The integration of observations across hemispheres and instruments also enabled detection of the faintest companions, ensuring that multiplicity was accurately characterized rather than underestimated. In this sense, the collaborative network functioned as a single, distributed observatory, transforming Earth into a coordinated platform for cosmic observation. The scale and sophistication of the collaboration highlighted the modern era of astronomy. Where past interstellar objects were studied primarily by individual telescopes or regional observatories, 3I Atlas demanded a planetary scale effort. Technology, logistics, and human expertise converged to produce an unprecedented level of precision in tracking, characterization, and analysis. This comprehensive approach not only allowed for real-time monitoring of the multiplying companions, but also established a framework for future interstellar events, demonstrating the capacity of the scientific community to respond rapidly and effectively to anomalies that challenge existing understanding. In this collaborative environment, the human narrative intertwined with the cosmic one. Each observation, each verified data point, was the result of countless decisions: where to point a telescope, how long to expose, which filters to apply, which models to run. Yet, amid the technical rigor, there was space for reflection. Astronomers marveled at the silent choreography of the swarm, tracing arcs through the void, indifferent to human scrutiny, yet revealing patterns that suggested hidden order. The act of collaboration became a meditation on both the universe and humanity's place within it. The multiplicity of objects mirrored the multiplicity of minds working in concert, each contributing perspective, skill, and insight to illuminate a phenomenon beyond comprehension. Ultimately, the collaboration underscored a fundamental principle. Understanding 3I Atlas and its companions required not just observation, but the synthesis of countless measurements into coherent models, the integration of diverse expertise, and the collective patience to interpret subtle anomalies. The swarm, moving silently through interplanetary space, had become a catalyst for global scientific engagement, drawing humans into a shared pursuit of knowledge that was as technical as it was profoundly human. Through this network of instruments and minds, the multiplying objects were transformed from faint points of light into a well-characterized system, their mysteries catalogued, measured, and appreciated, yet still compellingly beyond full explanation. With the multiplication of 3I Atlas now firmly established, the scientific community began exploring speculative explanations for the phenomenon, venturing beyond immediate observation into the realm of theoretical possibility. The data, hyperbolic trajectories, multiplicity, spectral heterogeneity, and subtle non-gravitational accelerations demanded hypotheses that could accommodate both the measured reality and the unusual characteristics of the companions. Among the first considerations were scenarios involving fragmentation. Could these objects be remnants of a single parent body disrupted in some distant stellar event? The notion of a parent body suggested an origin both coherent and complex, perhaps involving gravitational interactions with a massive star or tidal disruption near a dense astrophysical environment. One fragmentation scenario posited that 3I Atlas was a fragment of a larger exoplanetary body, dislodged from its system by gravitational perturbations and subsequently broken into multiple components during interstellar transit. In this model, the parent object might have experienced close encounters with nearby stars or tidal forces within a dense stellar cluster, causing it to fragment while maintaining a loosely coherent trajectory. This hypothesis could account for the multiplicity and alignment of companions, yet it struggled to explain the observed heterogeneity in spectral signatures. If all objects originated from a single parent, one might expect compositional uniformity. The observed variations implied either differentiation within the parent body or a more complex ejection mechanism. Another class of theories explored the possibility of interstellar debris clouds. In this framework, the companions were not fragments of a solid object, but elements of a dispersed cloud of small bodies ejected from a distant system. Over vast distances, interactions with radiation, stellar winds, and gravitational forces could maintain a quasi-coherent trajectory, allowing the cloud to arrive as a loosely associated group near the inner solar system. This model accounted for heterogeneity in size and composition, but introduced questions about stability. How could such a dispersed cloud remain sufficiently cohesive over millions of years to exhibit the alignment observed near Mars? The improbability of maintaining coherence added a layer of intrigue, reinforcing the idea that multiple mechanisms might be operating simultaneously. Some scientists speculated on the role of exotic astrophysical processes. Tidal disruption events, involving interactions with massive black holes or neutron stars, could theoretically eject multiple fragments at high velocity. These fragments might possess a range of compositions and shapes, reflecting differential forces during the disruption. In this scenario, the multiplicity and alignment of three I-Atlas companions could be interpreted as the result of a violent but organized ejection, a process operating on scales and energies far beyond typical planetary interactions. While intriguing, such events are rare, and the probability of a resulting swarm intersecting the solar system remains low, highlighting the extraordinary nature of the current observation. The possibility of interstellar aggregation also emerged as a speculative avenue. Could the companions represent bodies formed independently, yet influenced by subtle forces in interstellar space, such as gravitational interactions with molecular clouds or magnetic fields, which gradually aligned their trajectories? Over millions of years, these influences might produce a quasi-coherent swarm capable of arriving near Mars simultaneously. While largely hypothetical, this model demonstrated the willingness of the scientific community to consider unconventional processes, acknowledging that the universe contains mechanisms not yet observed within the confines of the solar system. Astrophysical simulations played a crucial role in testing these hypotheses. Computational models incorporated parameters such as mass, density, radiation pressure, and interstellar medium drag to simulate potential formation and ejection scenarios. Researchers ran countless iterations, comparing predicted trajectories, velocity distributions, and alignments with observed data. Some models successfully reproduced partial aspects of the swarm's behavior, fragmentation patterns, or velocity dispersions, but none fully captured the combination of multiplicity, coherence, spectral diversity, and non-gravitational acceleration. These simulations underscored the complexity of the phenomenon and highlighted gaps in current theoretical frameworks, reinforcing both the challenge and the allure of 3I-Atlas. Beyond purely physical explanations, some theorists cautiously entertained speculative interactions with interstellar environmental factors. Sparse gas, cosmic rays, or magnetic fields could exert subtle influences on low-mass bodies over long durations. While such forces are weak compared to gravity, their cumulative effect over millions of years might partially account for deviations or subtle alignment among companions. This line of reasoning emphasized the need to consider interstellar space not as an empty void, but as a medium capable of influencing objects in unexpected ways. Even if minor, these environmental interactions could contribute to the observed patterns, highlighting the interplay between local dynamics and interstellar context. The role of solar influence was also evaluated. As the companions approached the inner solar system, radiation pressure and solar wind could produce accelerations or rotational effects, particularly on small, low-mass bodies. By integrating thermal models, albedo measurements, and shape estimates, scientists calculated potential deviations from gravitational expectations. For some companions, these effects plausibly explained a portion of the observed acceleration. For others, residual anomalies persisted, hinting at intrinsic properties or interactions that remain unmodeled. The combination of multiple influences, fragmentation, history, interstellar environment, and solar interactions suggested that the phenomenon's complexity arises from the cumulative effect of numerous subtle factors rather than a single dominant mechanism. Philosophically, these speculative explanations illuminated the nature of uncertainty in science. The multiplicity of 3I-Atlas companions forced researchers to balance empirical observation with theoretical creativity, acknowledging that some aspects of the phenomenon might remain unresolved for years or decades. In this tension between what is known and what is hypothesized, the swarm became more than a scientific curiosity. It was a symbol of the limits of human understanding and the necessity of imaginative, interdisciplinary approaches. Each proposed model, whether fragmentation, debris cloud, or exotic ejection, represented a tentative step toward comprehension, constrained by observation yet enriched by speculation. The multiplicity also provoked reflection on scale and probability. Interstellar objects are rare, and multiple arrivals, aligned in trajectory and exhibiting coherent behavior, are rarer still. Statistical analysis suggested that observing such a swarm near Mars is extraordinarily unlikely, implying either an exceptional event or a process previously unrecognized in astrophysical theory. This improbability fueled both excitement and caution. While the phenomenon was real and measurable, understanding its origins required humility, patience, and recognition that the cosmos often operates beyond the bounds of expectation. Ultimately, the speculative origins of 3I Atlas and its companions exemplify the interplay between observation and theory. The data provide concrete constraints, trajectories, composition, acceleration, while the explanations extend into the domain of plausibility and creative reasoning. Fragmentation, debris clouds, tidal disruptions, interstellar aggregation, and environmental interactions all offer partial insights, yet none provides a complete narrative. In this tension, science demonstrates both its power and its humility. The ability to measure and describe, coupled with the recognition that some phenomena, especially on interstellar scales, may elude definitive understanding. The swarm of 3I Atlas thus stands as a reminder that the universe is not merely observed but interpreted, a vast and intricate reality whose deepest processes invite continuous inquiry and wonder. With speculation mounting about the origins of 3I Atlas and its companions, scientists began to consider potential risks and interactions within the inner solar system, particularly near Mars. While the objects were small, mere hundreds of meters at most, their hyperbolic trajectories and multiplicity raised questions about gravitational perturbations, collision probabilities, and long-term stability. Early models indicated that direct impact with Mars was highly improbable, yet even minimal gravitational interactions could subtly alter orbits, influencing future trajectories and potentially offering a rare opportunity to study interstellar object dynamics in situ. This phase of analysis combined rigorous orbital mechanics with probabilistic modeling, highlighting the interplay between empirical measurement and predictive simulation. Researchers constructed detailed N-body simulations to explore the potential interactions of the swarm with planetary bodies. Each companion was treated as an individual entity, with gravitational influences from Mars, Earth, Jupiter, and the Sun incorporated into high-precision models. Even minor perturbations could propagate over astronomical distances, affecting trajectory predictions over months or years. The simulations consistently demonstrated that while collisions were unlikely, the swarm's passage through the inner solar system offered a unique laboratory for studying gravitational interactions at hyperbolic velocities. Observers were especially attentive to Mars, as its proximity allowed for more precise measurements of deflection and acceleration induced by planetary mass. Beyond immediate collision probabilities, scientists considered the cumulative influence of the swarm on the broader solar system. Each companion, while small, contributed infinitesimal perturbations to nearby minor bodies and dust populations. Over time, such interactions could generate measurable effects, particularly if additional interstellar objects arrived along similar trajectories. These analyses emphasize the principle that even seemingly minor actors can produce cascading effects in complex systems, a concept familiar in celestial mechanics yet made tangible by the presence of 3I Atlas and its companions. The potential for physical interaction with Mars itself sparked interest beyond orbit prediction. While direct impacts were unlikely, the possibility of near passes provided opportunities for observation, particularly in terms of gravitational lensing and photometric monitoring. Instruments on Mars-orbiting spacecraft, such as the Mars Reconnaissance Orbiter and the MAVEN probe, could detect subtle changes in reflected light or gravitational perturbations as the swarm passed nearby. By combining terrestrial and Martian observations, astronomers could refine models of mass, density, and structural properties for each companion, obtaining empirical data that would otherwise be inaccessible for interstellar objects. Spectroscopic and thermal monitoring during close approaches further enhanced scientific value. As the companions neared Mars, variations in illumination allowed for more precise characterization of surface features, rotational states, and potential sublimation activity. These measurements provided an unprecedented window into the physical behavior of small interstellar bodies in proximity to a planetary environment. Thermal data helped refine models of size, albedo, and heat retention, while repeated photometric monitoring revealed rotation periods and surface heterogeneity. The confluence of techniques allowed scientists to build a more complete understanding of the swarm, connecting orbital anomalies with compositional and structural properties. The consideration of potential risk also extended to human space exploration. While crewed missions to Mars were still in planning stages, understanding the passage of interstellar objects became relevant for trajectory planning and hazard assessment. Even small particles released through outgassing or fragmentation could pose risks to spacecraft operating near the planet. Simulations accounted for dust ejection rates, particle trajectories, and potential impact energies, allowing mission planners to incorporate contingencies for close approaches. In this sense, the presence of 3I Atlas and its companions intersected with practical considerations of human exploration, linking interstellar observation with applied planetary science. The swarm also provoked reflections on the dynamical boundaries of the solar system. Observing objects with hyperbolic trajectories interacting subtly with planetary bodies illustrated the permeability of the solar system to interstellar material. These interactions, though minimal in immediate consequence, highlighted the continuous exchange of matter across cosmic distances. Over astronomical timescales, such exchanges influence planetary surfaces, minor body populations, and potentially even the delivery of prebiotic compounds. The passage of 3I Atlas thus served as a microcosm of interstellar material flow, offering insight into processes that shape not only individual objects, but also the broader dynamical architecture of planetary systems. Probabilistic modeling was crucial for understanding uncertainties associated with the swarm's passage. Each companion's trajectory carried inherent observational errors, minute uncertainties in position, velocity, and acceleration. Monte Carlo simulations and other stochastic methods were employed to explore the range of possible outcomes, generating confidence intervals for near-approach distances, orbital deflections, and interaction timescales. These models revealed that while catastrophic events were exceedingly unlikely, subtle perturbations remained possible, underscoring the importance of continuous observation and iterative refinement of predictions. The consideration of potential risks naturally dovetailed with opportunities for scientific exploitation. Close approaches to Mars provided conditions under which mass, density, and compositional measurements could be validated. By observing gravitational deflection or minute variations in trajectory, scientists could refine their understanding of interstellar object physics. Similarly, high-resolution spectral and thermal monitoring during approach allowed for cross-validation of ground-based observations, offering an unparalleled opportunity to correlate theoretical models with empirical data. The interplay of risk and reward emphasized that the multiplicity of the swarm was not merely a curiosity, but a gateway to deepened understanding of interstellar dynamics. Finally, the analysis of potential threats highlighted a philosophical dimension. The solar system, while stable on human timescales, is constantly traversed by objects originating from beyond, bringing with them the unpredictable influence of interstellar processes. The passage of 3I, Atlas, and its companions reminded observers of the fragility and dynamism inherent in cosmic systems. Even objects of modest size can produce meaningful effects over long timescales or through subtle gravitational interactions. The phenomenon encouraged a reflection on human perception of safety and scale, underscoring that the universe operates with autonomy, often beyond immediate comprehension, and that understanding these interactions requires both meticulous observation and humility in interpretation. In sum, the potential threat assessment of 3I Atlas and its companions combined rigorous orbital modeling, probabilistic analysis, and interdisciplinary observation to produce a nuanced understanding of both risk and opportunity. While direct collisions with Mars were improbable, the swarm's passage provided an extraordinary opportunity to study interstellar object dynamics in situ. Gravitational perturbations, thermal and spectral monitoring, and comparative analysis across multiple companions allowed scientists to extract insights far beyond what single-object observations permit. The phenomenon thus exemplified the dual nature of cosmic encounters, simultaneously a potential source of risk and a profound avenue for discovery, highlighting the intricate interplay between interstellar dynamics and planetary environments. The multiplicity and anomalous behavior of 3I Atlas and its companions prompted scientists to investigate the subtle gravitational interactions shaping their motion. While their hyperbolic trajectories indicated interstellar origin, the approach to the inner solar system introduced perturbations from planetary masses, particularly Mars and Jupiter. Understanding these influences required a careful balance of observational precision and theoretical modeling. Researchers needed to account for classical gravitational forces, the collective interactions among companions, and any subtle non-gravitational accelerations to construct a coherent picture of orbital evolution. The first step involved high-fidelity N-body simulations. Each companion was treated as an individual particle, with mass estimates derived from photometric and infrared observations. Perturbative influences from the Sun, Mars, Jupiter, and other planets were incorporated, along with mutual gravitational effects among companions. These models revealed complex interactions. Slight deviations in velocity propagated over millions of kilometers, altering predicted positions in ways not immediately intuitive. Even small changes in mass assumptions or initial conditions produced noticeable divergences in trajectory predictions, highlighting the sensitivity of orbital behavior in multi-object systems. The simulations also revealed unexpected patterns of resonance and clustering. Despite independent hyperbolic velocities, some companions exhibited transient alignments, forming ephemeral chains in space that persisted for days or weeks before dispersing. These patterns suggested that the object's collective gravitational interactions, although weak compared to planetary influences, were sufficient to produce temporary coherence. This phenomenon mirrored, in miniature, the behavior of larger systems such as asteroid families or planetary rings, yet occurring under hyperbolic, interstellar conditions that were largely unprecedented in observational history. Planetary perturbations, particularly from Mars, were analyzed in detail. As each companion passed within a few million kilometers of the planet, its trajectory experienced minute deflections. While these were far too small to pose impact threats, they provided invaluable data. Measuring the deflection allowed researchers to infer mass estimates, surface properties, and rotational states. For instance, objects exhibiting unexpected lateral acceleration during planetary flybys suggested anisotropic mass distribution or irregular shape, correlating with spectroscopic evidence of heterogeneous composition. In this way, gravitational interactions became a diagnostic tool, linking orbital dynamics with physical characteristics. The influence of Jupiter, with its immense mass, introduced additional complexity. Even when companions remained distant, its gravitational field subtly perturbed hyperbolic paths, producing long-period variations that could only be modeled over extended simulations. These perturbations required the integration of high-precision ephemerides and the consideration of Jupiter's own orbital eccentricity. By comparing observed motion with simulated predictions, scientists were able to identify residual accelerations inconsistent with gravitational effects alone, reinforcing the role of non-gravitational forces and prompting further investigation into surface properties and environmental interactions. Mutual gravitational interactions among companions, though comparatively weak, also contributed to trajectory evolution. The cluster's small mass limited the magnitude of these effects, yet over the distances and timescales involved, slight accelerations and deflections accumulated, producing subtle deviations from isolated hyperbolic paths. Observationally, these manifested as minor shifts in position that, when aggregated across multiple companions, revealed a dynamic interplay of forces within the swarm. This reinforced the notion that the multiplicity was not merely a statistical anomaly, but a real, interacting system, sensitive to both internal and external influences. Beyond classical gravitational modeling, researchers considered tidal and rotational effects. Rapid rotation, or irregular shapes, can induce torque that subtly modifies trajectories, particularly in low-gravity environments. Spectroscopic and photometric data indicated that some companions were likely tumbling or rotating irregularly, suggesting that spin-induced forces contributed to observed deviations. These rotational dynamics, combined with external perturbations, created a multidimensional problem in orbital prediction, necessitating iterative modeling and continuous observational refinement. Gravitational analysis also intersected with long-term predictive modeling. By projecting trajectories months and years into the future, scientists evaluated the potential evolution of the swarm after passing Mars. Simulations indicated that companions would disperse gradually due to the combined effects of planetary perturbations and internal interactions, eventually blending back into the interstellar medium. This dispersal highlighted the transient nature of the phenomenon. The swarm's coherent appearance near Mars was a fleeting event, a brief window during which the complex interplay of interstellar origin and planetary influences became observable. The investigation of gravitational interactions emphasized the limitations of classical celestial mechanics when applied to interstellar phenomena. Standard orbital models excel in predicting motions of bound solar system objects, yet hyperbolic trajectories, multiplicity, and non-gravitational effects required extensions to conventional theory. Researchers incorporated radiation pressure, outgassing, and potential interstellar medium drag into simulations, creating hybrid models capable of capturing the nuanced behavior observed. Even so, residual anomalies persisted, suggesting that additional, as yet unmodeled forces or properties were influencing motion. Beyond technical implications, the gravitational analysis carried a profound philosophical dimension. Observing how minute forces shaped the motion of companions underscored the delicate balance governing celestial systems. Hyperbolic velocities, planetary perturbations, and internal interactions combined to create transient patterns of alignment and dispersion, demonstrating the sensitivity of cosmic dynamics to initial conditions. For astronomers, the multiplicity of three I-Atlas companions became a meditation on order and chaos, on the thin line between predictable physics and emergent complexity. Even in a vast, seemingly empty void, subtle interactions produced observable consequences, revealing the universe as both lawful and intricate. In practice, these gravitational studies informed broader observational strategy. Predictions of near-approach distances, alignment windows, and potential accelerations guided telescope scheduling, ensuring that data collection maximized coverage during periods of dynamic change. Observatories coordinated to capture critical moments, such as closest passes to Mars or relative alignment among companions, allowing for cross-validation of models and refinement of mass, size, and rotational estimates. This integration of gravitational modeling with observational logistics exemplified the synergy between theory and measurement, demonstrating how the study of interstellar phenomena relies on both predictive simulation and empirical verification. Ultimately, the analysis of gravitational interactions illuminated the depth and complexity of three I-Atlas's journey through the solar system. Hyperbolic trajectories, planetary perturbations, mutual interactions, and subtle accelerations converged to produce motion that was simultaneously measurable and enigmatic. The swarm's behavior highlighted the dynamic interplay of forces operating across vast distances, emphasizing both the capacity of science to quantify celestial mechanics and the limits of existing models when confronted with unprecedented phenomena. In this delicate dance of gravity and motion, the multiplicity of three I-Atlas companions revealed the universe's capacity for subtlety, intricacy, and mystery, inviting continued observation, modeling, and reflection. As observational data accumulated, astronomers began to notice patterns emerging among the three Atlas companions that hinted at subtle spatial organization. While their hyperbolic trajectories confirmed their interstellar origin and the multiplicity indicated a non-random occurrence, detailed mapping revealed faint alignments and clustering in three-dimensional space. These patterns were neither rigid nor perfectly predictable, yet they were persistent, suggesting influences beyond immediate planetary gravitational forces and implying either a coordinated origin or the cumulative effect of interstellar processes operating over immense timescales. The recognition of such patterns added a new layer of complexity to the mystery, raising questions about formation mechanisms, prior interactions, and possible unseen forces. Analysis of positional data over successive nights indicated that while the companions moved independently, certain subgroups maintained relative proximity over extended periods. This clustering suggested that the objects were not entirely dispersed fragments, but retained a faint coherence, possibly reflecting a shared origin or a dynamical interaction in the interstellar medium. Astronomers employed statistical methods to quantify alignment, measuring deviations from random distribution and testing the likelihood of observed configurations arising by chance. Results indicated that the clustering was significant, reinforcing the notion that the swarm's arrangement carried meaningful information about past history or underlying physical processes. The observed patterns prompted consideration of tidal and fragmentation scenarios. If three I-Atlas originated from a larger parent body disrupted in a distant stellar encounter, gravitational forces could have produced fragments with initial velocities and angular distributions that naturally aligned over long distances. Subsequent interstellar travel, influenced by radiation pressure and sparse interactions with cosmic dust or gas, could preserve partial alignment while allowing gradual divergence. In this framework, The spatial patterns observed near Mars represented the residual imprint of processes occurring millions of years prior, offering a rare glimpse into the long-term evolution of interstellar debris. Alternatively, some scientists considered environmental influences during transit through the galaxy. Interstellar magnetic fields, though weak, can exert small forces on conductive or charged surfaces over extended periods. Similarly, interactions with sparse molecular clouds could induce subtle gravitational perturbations. While individually negligible, these cumulative effects over millions of years might influence trajectories enough to produce the faint alignments observed. Such considerations underscored the subtlety of interstellar dynamics, demonstrating that even the apparent randomness of deep space can yield coherent patterns when viewed at the appropriate scale and with precise observation. The multiplicity and clustering also raised questions about potential interactions among companions themselves. Mutual gravitational attraction, while minimal due to the small masses involved, could influence relative motion over time. Observations suggested that some pairs or small groups exhibited correlated accelerations, indicating weak but detectable interactions. This internal coherence, combined with external influences, created a dynamic system whose motion was neither entirely predictable nor wholly chaotic. The complexity challenged the assumption that interstellar objects behave independently once ejected from their origin systems, suggesting that subtle interactions can preserve alignment or structure over interstellar distances. Photometric and spectroscopic data complemented the spatial analysis, revealing correlations between composition and patterning. Some clusters shared similar spectral signatures, hinting at a common parentage or exposure history, while others exhibited heterogeneity, implying multiple sources or differential surface evolution. The alignment of certain compositional types with spatial clusters suggested that fragmentation processes may have been selective, perhaps influenced by internal structure or rotational dynamics of the parent body. These insights emphasized that spatial patterns were not merely geometrical, but intimately tied to the physical and chemical properties of the companions, creating a multidimensional tapestry for study. Advanced computational modeling became essential to interpret these observations. Researchers employed simulations that integrated orbital mechanics, non-gravitational forces, and interstellar environmental effects to test the plausibility of various formation and evolution scenarios. Monte Carlo methods allowed exploration of vast parameter spaces, varying initial fragment velocities, composition-dependent outgassing rates, and cumulative radiation effects. These models reproduced certain observed alignments under specific conditions, supporting hypotheses of partial coherence preserved over long-term interstellar travel. Yet no model fully captured the combination of multiplicity, spectral diversity, and alignment, highlighting the limits of current understanding and reinforcing the enigmatic nature of the swarm. The emergent patterns also carried philosophical and aesthetic significance. Observing faint alignments across millions of kilometers evoked a sense of cosmic choreography, a delicate balance between randomness and order. The companions, though individually small and seemingly insignificant, collectively traced a silent, ephemeral architecture in space, a fleeting testament to forces operating on scales far beyond human perception. This visual and conceptual coherence inspired reflection on the interplay between determinism and chance in the universe, illustrating that even in the apparent void of interstellar space, structure and pattern can arise from subtle interactions over immense distances and timescales. Beyond scientific analysis, the discovery of spatial patterns influenced observational strategy. Recognizing potential alignments allowed astronomers to predict locations of faint companions more accurately, optimizing telescope pointing and scheduling. By anticipating likely trajectories and relative positions, observers could detect objects otherwise too dim or transient to identify individually. This predictive capability exemplified the feedback loop between data and observation. Emergent patterns informed strategy, which in turn generated new data, refining models and deepening understanding. The recognition of spatial patterning also reframed hypotheses about origin. If the companions exhibited coherence inconsistent with random dispersal, it strengthened arguments for a shared origin or structured ejection mechanism. Whether from a fragmented parent body, a tidal disruption event, or a dynamic interstellar cloud, the patterns suggested a level of organization that extended across light years and millions of years of travel. This insight shifted theoretical focus from isolated object behavior to systemic dynamics, emphasizing that interstellar phenomena cannot always be understood in isolation, but must be interpreted in the context of collective behavior and long-term evolution. Ultimately, the observation of clustering and spatial alignment illuminated the hidden order underlying the swarm's seemingly chaotic motion. It suggested that 3I Atlas and its companions were more than a collection of random fragments. They were participants in a dynamic system shaped by history, physics, and interstellar forces. The patterns revealed the subtle interplay between gravitational interactions, environmental influences, and internal properties, demonstrating that even in the depths of interstellar space, structure and coherence can emerge. For astronomers, these emergent alignments transformed the multiplicity from a statistical curiosity into a source of insight, providing tangible evidence of interstellar processes that operate over unimaginable distances and timescales, and reinforcing the profound complexity of the universe. The anomalous behavior of 3I Atlas and its companions inevitably led scientists to explore connections with fundamental physics, invoking principles derived from Einsteinian relativity and the broader frameworks of modern astrophysics. While classical Newtonian mechanics accounted for much of the motion observed, subtle deviations and high-velocity trajectories demanded consideration of relativistic effects, particularly in terms of time dilation, energy distribution, and the propagation of gravitational influences. Though the velocities of the companions were far below the speed of light, their interstellar origin, coupled with the hyperbolic nature of their orbits, introduced circumstances under which relativistic corrections, while small, could become significant in high-precision modeling. One area of investigation involved the potential impact of general relativity on trajectory predictions. Close approaches to planetary bodies, especially Mars and Jupiter, created opportunities to observe minute relativistic effects on hyperbolic paths. While these effects were subtle, manifesting as tiny deviations in predicted position over time, they provided a testbed for high-precision modeling. Incorporating general relativistic corrections allowed scientists to refine simulations, improving the alignment between predicted and observed positions. Moreover, these adjustments highlighted the necessity of extending classical gravitational models when studying interstellar objects passing through complex planetary systems. Relativity also framed considerations of energy and momentum distribution within the swarm. Each companion possessed kinetic energy far exceeding that of typical solar system bodies of comparable size, reflecting their interstellar velocities. Understanding how this energy was distributed and how interactions with radiation or planetary fields might influence momentum required integration of relativistic principles with classical dynamics. For example, even minor energy exchanges during close planetary flybys could produce measurable changes in velocity or rotation, detectable through careful astrometric observation. These analyses underscored that the swarm's behavior could not be fully captured without accounting for the nuances of high-velocity motion over astronomical distances. Einstein's insights into the curvature of space-time also inspired reflections on the broader implications of interstellar trajectories. While the companions were not approaching relativistic speeds, their motion through the solar system modulated by the combined gravitational fields of multiple planets, and the Sun offered a tangible illustration of how mass curves space-time, subtly guiding the paths of small bodies. This served as both a practical modeling consideration and a philosophical touchstone. Even objects millions of kilometers away are influenced by the geometry of the gravitational landscape, moving along paths shaped by both mass and the fabric of space itself. The swarm's subtle accelerations and deviations prompted consideration of frame-dragging effects and other higher-order relativistic phenomena. Though these influences were exceedingly small, the precision of modern observations rendered them detectable, at least in principle. By integrating such corrections into simulations, scientists could explore whether unexplained accelerations might partially arise from relativistic interactions with the rotating gravitational fields of planets. While not a primary driver of the observed anomalies, these effects reinforced the necessity of comprehensive modeling that incorporates all relevant physics, particularly when interpreting deviations that challenge conventional expectations. Beyond classical and relativistic mechanics, the 3I Atlas phenomenon invoked broader questions about the nature of space itself. The object's hyperbolic velocities, multiplicity, and alignment hinted at interactions with the interstellar medium, radiation fields, and possibly unseen forces. While speculative, such considerations naturally intersected with Einsteinian principles, suggesting that the propagation of energy, momentum, and information in the universe is governed not solely by Newtonian intuition, but also by relativistic constraints. Modeling the swarm's behavior thus became an exercise in unifying observation with theory, connecting empirical data to fundamental laws of physics. The high precision required for these analyses also illuminated the limits of measurement. Observational uncertainty, even at the level of milliarcseconds, could influence interpretations of relativistic effects or subtle accelerations. Consequently, astronomers emphasized rigorous error analysis, combining datasets from multiple telescopes to mitigate instrumental biases and atmospheric distortion. Statistical modeling and covariance analysis allowed for the quantification of confidence intervals, ensuring that relativistic corrections were applied only within the bounds justified by data. This meticulous approach reflected a balance between theoretical ambition and empirical caution, a hallmark of modern astrophysical inquiry. Relativity further influenced interpretations of potential interstellar forces acting upon the swarm. Interactions with cosmic radiation, magnetic fields, or diffuse gas in the interstellar medium can, over millions of kilometers, produce cumulative effects on small bodies. Though classical mechanics can approximate these forces, relativistic treatments provide a more accurate framework for understanding the propagation of energy and momentum across spacetime. In modeling these interactions, scientists incorporated corrections for energy transfer, velocity-dependent forces, and the influence of spatial curvature, producing more robust simulations capable of capturing the swarm's nuanced behavior. The application of Einsteinian principles also facilitated comparative analysis with prior interstellar objects. Oumuamua, for instance, exhibited non-gravitational acceleration that sparked debates about radiation pressure, cometary outgassing, and other subtle forces. By framing 3I Atlas Within the context of relativistic and classical physics, astronomers could evaluate whether similar mechanisms might operate across multiple objects or whether unique properties of the swarm multiplicity, alignment, or composition necessitated novel explanations. This comparative approach reinforced the integration of theoretical physics with observational astrophysics, emphasizing that anomalies provide both challenges and opportunities for refining fundamental understanding. Finally, the consideration of relativistic effects invited philosophical reflection on humanity's engagement with the cosmos. Observing objects moving at interstellar velocities, influenced by planetary gravities and subtle environmental forces, highlights the intricate interplay of motion, energy, and space across scales far beyond direct human experience. The companion's trajectories offer a tangible illustration of principles that govern all matter, linking distant observation with the fundamental geometry of the universe. Einsteinian mechanics thus provided both a practical framework for modeling and a lens through which to contemplate the interconnectedness of cosmic phenomena, revealing that even faint points of light carry profound implications for our understanding of space, time, and the subtle orchestration of celestial dynamics. The presence of 3I Atlas and its multiplying companions naturally prompted comparisons with some of the most profound insights of Stephen Hawking and other theoretical physicists who had explored the deep structure of the cosmos. While Einstein provided the mathematical framework for space-time curvature, Hawking's work on black holes, quantum fields, and cosmic uncertainty offered a lens through which to consider the broader implications of objects traversing interstellar space. Although these companions were not approaching event horizons or relativistic extremes, their hyperbolic trajectories and multiplicity resonated with questions about the nature of matter, energy, and information across vast cosmic distances. Hawking's studies of black holes and Hawking radiation emphasized the interaction between extreme gravitational fields and quantum mechanics, highlighting that even regions thought to be empty or uniform can harbor subtle, non-intuitive effects. In the context of 3I Atlas, the analogy was conceptual rather than direct. The companion's passage through space, influenced by interstellar forces, radiation pressure, and planetary gravities, illustrated how small, seemingly insignificant bodies can be subtly altered by distant interactions. Their motion reminded scientists that the universe is a dynamic web, in which even objects moving far from massive gravitational sources experience cumulative effects over time, analogous to how Hawking had demonstrated that black holes are not isolated, but radiate and interact with their surroundings in ways that challenge classical assumptions. One area of reflection concerned entropy and the evolution of small bodies in interstellar space. Over millions of years, these objects traverse environments of varying density, temperature, and radiation. Cosmic rays bombard their surfaces, micrometeoroid impacts chip away at structure, and exposure to ultraviolet light alters chemical composition. Hawking's work on the inevitability of entropy and the probabilistic nature of particle interactions provided a philosophical framework for understanding how the companion's surfaces and internal structures might evolve during their interstellar journey. Each object, while appearing inert and frozen, carries the imprint of countless interactions, a silent record of cosmic history encoded in material properties and orbital behavior. The swarm's multiplicity suggested a system that, while fragile, had persisted across time and space, surviving ejection from a distant stellar system, interstellar transit, and approach through the solar system's gravitational milieu. From a Hawking-inspired perspective, one could consider the probabilistic challenges such bodies face. The cumulative likelihood of collision, disruption, or evaporation over millions of years is non-negligible. that such a system remained coherent enough to be observable near Mars emphasizes the delicate balance of forces and probabilities at work in the cosmos. The companions thus became exemplars of persistence amid entropy, surviving in the interstellar medium long enough to intersect with a planetary system billions of kilometers away. Hawking's insights into quantum fluctuations and the nature of vacuum energy provided additional conceptual resonance. While the companions' motions were not governed by quantum phenomena on a macroscopic scale, the idea that even empty space possesses subtle structure, energy, and influence mirrors the subtle accelerations and deviations observed in the swarm. Radiation pressure, interstellar magnetic fields, and interactions with sparse particles operate on a scale that is weak compared to gravity, yet cumulatively capable of altering trajectories. These phenomena exemplify how small-scale forces, analogous in concept to vacuum fluctuations, can produce observable effects over astronomical distances and timescales. The philosophical implications of Hawking's work extend to the multiplicity itself. If the companions originated from a disrupted system, their survival and partial coherence might be interpreted as a manifestation of cosmic resilience within a universe governed by probabilistic laws. The alignment of certain companions, the persistence of hyperbolic trajectories, and the subtle non-gravitational accelerations together reflect a system navigating the tension between determinism and randomness, order and chaos. Hawking's explorations of information preservation in black holes resonate metaphorically. Just as information is conserved in unexpected ways in extreme environments, the swarm preserves information about its origin, formation, and interstellar journey, encoded in position, velocity, and composition. The swarm also invited reflection on the universality of physical law. Hawking emphasized that the laws of physics operate consistently, even in extreme conditions or across cosmic distances. Observing 3I Atlas and its companions reinforces this principle. Despite their interstellar origin, despite their complex multiplicity, and despite subtle anomalies in acceleration, their motion remains intelligible within the frameworks of classical and relativistic physics, with small deviations accounted for by environmental influences. This consistency, however, does not diminish the sense of wonder. It highlights that the universe can simultaneously be lawful and deeply surprising, producing phenomena that challenge both observation and imagination. Connections to cosmology were also compelling. Hawking's work on the origin of the universe, cosmic inflation, and the probabilistic nature of spacetime frames the companions as participants in a vast, ongoing process. These objects, having traveled perhaps millions of light-years from their point of origin, serve as tangible messengers from other star systems. They traverse regions shaped by gravitational waves, interstellar gas dynamics, and radiation fields, each journey a microcosm of cosmic evolution. Observing them allows scientists to probe conditions beyond the solar system, offering empirical touchpoints that intersect with theoretical frameworks about the large-scale structure of the galaxy and the distribution of interstellar material. Furthermore, the multiplicity evokes questions about the prevalence of interstellar matter. While single interstellar objects have been documented previously, the appearance of multiple companions suggests that clusters may occasionally traverse planetary systems. Hawking's insights into probability and statistical mechanics offer a conceptual lens. The universe, governed by probabilistic processes, occasionally produces low-likelihood events that nevertheless manifest within observable timeframes. The presence of multiple 3I Atlas companions exemplifies such an occurrence, highlighting both the rarity and the inevitability of extraordinary events within a vast probabilistic landscape. Finally, reflecting on Hawking's broader legacy, emphasizes the emotional and philosophical resonance of the swarm. The companions' hyperbolic, multiplying paths, their subtle accelerations, and their preserved coherence across vast distances serve as reminders that the universe is at once comprehensible and inscrutable. They illustrate the tension between observation and interpretation, data and mystery, law and chance. Just as Hawking's theoretical explorations transformed our understanding of black holes and cosmology, the swarm challenges and expands our appreciation of interstellar dynamics, prompting both technical investigation and profound reflection on humanity's place within a cosmos that is simultaneously ordered and unpredictable. The extraordinary motion and multiplicity of 3I Atlas companions demanded a new level of computational simulation to reconcile observation with theory. Researchers turned to high-fidelity modeling to replicate both hyperbolic trajectories and subtle anomalies in acceleration and alignment. This phase of study required integration across multiple scales: orbital dynamics, rotational states, radiation pressure, interstellar environmental effects, and even potential minor collisions. By simulating thousands of possible histories, scientists sought to identify plausible scenarios that could account for the observed behavior while remaining consistent with fundamental physical laws. Central to this modeling effort was the incorporation of multi-body dynamics. Unlike solitary interstellar objects, the swarm's companions interacted weakly but measurably with one another. Each object's motion influenced nearby companions, producing temporary correlations in velocity and minor deflections in trajectory. Simulations accounted for these interactions by representing each companion as a discrete particle with estimated mass, shape, and reflectivity. Newtonian gravitational equations were coupled with perturbative terms for solar radiation and potential outgassing, creating a hybrid model capable of capturing subtle, cumulative effects. The resulting simulations revealed that even small variations in initial conditions could lead to significantly different spatial patterns over interstellar distances, highlighting the sensitivity and complexity inherent in the system. Non-gravitational forces were a major focus of the simulation work. Observational evidence suggested that some companions experienced accelerations inconsistent with gravity alone, prompting inclusion of forces such as radiation pressure, anisotropic sublimation, and potential interactions with charged particles in the interstellar medium. For instance, outgassing of volatile compounds could produce minute thrusts, gradually altering trajectories over days or weeks. Similarly, radiation pressure could differentially affect objects depending on albedo, size, and surface geometry. By integrating these factors, models produced realistic deviations in motion, allowing comparison with observed positional data. While the agreement was not perfect, the simulations successfully reproduced key anomalies, supporting the hypothesis that multiple subtle forces combined to shape the companions' paths. Rotational dynamics were also integrated into the models. Photometric observations indicated that several companions were tumbling or rotating irregularly, potentially producing variable cross-sectional areas exposed to solar radiation. These variations affect both radiation pressure and thermal recoil forces, introducing time-dependent accelerations. Simulations accounted for rotational states, orientation angles, and shape asymmetry, revealing that spin dynamics could contribute meaningfully to observed deviations in velocity. In some cases, rotationally induced accelerations aligned with patterns seen in positional data, suggesting a complex interplay between physical structure, surface properties, and orbital behavior. The simulations were computationally intensive, requiring distributed processing across multiple supercomputing facilities. Thousands of parameter combinations were tested, varying initial velocities, mass distributions, surface reflectivity, and interstellar environmental factors. Monte Carlo methods allowed researchers to explore probabilistic outcomes, quantifying the likelihood of different alignment patterns and acceleration anomalies. Each iteration provided insight into which combinations of forces and histories could plausibly produce the observed behavior, guiding observational priorities and refining theoretical understanding. The emergent behavior from these models offered new perspectives on the swarm's origin. Fragmentation scenarios, for example, could produce multiplicity and partial alignment if initial conditions were carefully constrained. In such models, variations in composition, shape, and rotational state naturally led to differences in acceleration and spectral properties, aligning with observational data. Other simulations explored the possibility of interstellar debris clouds, with loosely associated objects gradually converging along similar hyperbolic paths. These models demonstrated that multiplicity could arise from either cohesive origin events or statistical convergence in a dynamically structured interstellar medium. One notable outcome of the simulations was the ability to predict future positions with unprecedented accuracy. By integrating orbital, non-gravitational, and environmental forces, researchers generated forecast trajectories for each companion, including expected near-approach distances to Mars and potential interactions with other solar system bodies. These predictions informed observational scheduling, ensuring that telescopes captured critical moments when multiple companions were simultaneously visible or when anomalies in motion were most pronounced. The feedback loop between simulation and observation allowed continuous refinement of models, exemplifying the iterative nature of scientific inquiry in the face of complex phenomena. The modeling work also highlighted limitations in current understanding. Despite sophisticated simulations, residual discrepancies remained between predicted and observed positions, particularly for the faintest companions. These deviations underscored that unknown factors, whether physical properties, environmental interactions, or observational uncertainties, still influenced the system. Recognizing these limitations, researchers approached conclusions with caution, emphasizing probabilistic interpretation rather than definitive claims. This humility reinforced the philosophical dimension of the study. The universe often presents phenomena that resist complete comprehension, even when analyzed with the most advanced tools. Beyond the technical results, the simulations revealed a deeper insight into cosmic dynamics. The apparent organization of the swarm, with transient clusters and partial alignment, emerged naturally from the interplay of multiple weak forces acting over vast distances. What initially seemed chaotic or anomalous revealed a subtle order when modeled comprehensively. The companion's motion demonstrated how small-scale interactions, compounded by interstellar forces and internal properties, can produce emergent patterns observable even from billions of kilometers away. This emergent behavior mirrored broader themes in astrophysics, where complexity often arises from the cumulative effect of simple physical principles applied across immense scales. The simulation phase also reinforced the importance of interdisciplinary collaboration. Orbital mechanics, specialists, computational physicists, material scientists, and observational astronomers all contributed to model development, parameter selection, and validation. Photometric and spectroscopic data informed assumptions about mass, shape, and surface properties, while N-body simulations tested dynamic outcomes over extended timescales. This integrated approach exemplified the modern methodology required to study interstellar phenomena, where no single perspective suffices and where collaboration amplifies both understanding and predictive capability. Ultimately, the computational modeling of 3I Atlas and its companions transformed observational data into a coherent narrative. The simulations provided plausible scenarios for the swarm's origin, explained key anomalies in motion, and enabled accurate forecasts for future observation. Yet, even as models aligned with data, they preserved the mystery. Subtle deviations remained, multiplicity was partially explained, but not fully, and the swarm continued to inspire both technical inquiry and philosophical reflection. The modeling phase, bridging empirical measurement and theoretical exploration, underscored the dynamic interplay of known forces, environmental influences, and emergent patterns, revealing the complexity and beauty inherent in interstellar phenomena. The curious possibility that 3I, Atlas, and its companions might be composed of exotic matter or possess unusual material properties became a focal point of theoretical investigation. Observations indicated that the swarm exhibited a combination of hyperbolic trajectories, subtle accelerations, and spectral heterogeneity that could not be fully explained by classical composition models. While ordinary silicates, ices, and dust could account for some features, residual anomalies in reflectivity, non-gravitational motion, and alignment patterns suggested that other, less familiar physical processes might be at play. The notion of exotic matter substances composed of unusual atomic arrangements or even hypothetical particle forms offered a speculative but scientifically grounded lens for interpreting these observations. One hypothesis considered low-density, highly porous structures, analogous to cometary fluffy aggregates, as a potential explanation for subtle accelerations observed in the companions. Such structures would have large surface areas relative to mass, making them particularly sensitive to radiation pressure and weak interstellar forces. If a companion were composed primarily of loosely bound dust and ices, the cumulative effect of solar radiation could produce measurable deviations from gravitational trajectories. Moreover, variations in porosity or internal cohesion among companions could account for the observed diversity in acceleration, alignment, and spin behavior. In this sense, exotic matter need not be fundamentally new to physics but could represent variations within known material categories that produce unusual macroscopic effects. Beyond low-density aggregates, researchers considered the possibility of objects containing highly reflective or unusual mineral phases. Spectral analyses suggested anomalies in reflectivity at certain wavelengths, hinting at surfaces that differed from typical silicate or icy bodies. Materials with extreme albedo could enhance the effect of radiation pressure, producing accelerations inconsistent with standard mass estimates. The combination of reflective surfaces, irregular shape, and rotational motion could generate complex, time-dependent deviations in motion, potentially explaining some of the residual anomalies that persisted despite classical modeling. These considerations exemplified the intersection of composition, structure, and dynamics, illustrating how material properties can subtly but significantly influence observable behavior. A more speculative avenue involved interactions with dark matter or other hypothetical components of the interstellar medium. While dark matter is typically considered weakly interacting over interstellar distances and timescales, even minimal interactions could cumulatively affect low-mass, highly responsive bodies. If the companions possessed unusual composition or charge distributions, they might experience differential acceleration as they moved through regions with variable dark matter density or electromagnetic fields. Although highly conjectural, this line of reasoning emphasized that the swarm's motion might encode information not only about its immediate environment, but also about the broader structure of the galaxy and the distribution of matter beyond ordinary detection. Thermal and spectroscopic measurements provided additional constraints. Infrared observations indicated varying surface temperatures and emission profiles among companions, suggesting differences in composition, albedo, and perhaps internal structure. Some companions displayed unexpectedly efficient reflection of sunlight, while others absorbed and re-radiated energy in patterns inconsistent with simple models of rock or ice. Integrating these data into simulations allowed researchers to test the plausibility of exotic material compositions, assessing how density, reflectivity, and surface structure influenced trajectory deviations and alignment patterns. While results remained inconclusive, the approach offered a structured framework for evaluating unconventional explanations grounded in observable phenomena. Laboratory analogues on Earth also informed modeling. Experiments with porous aggregates, reflective powders, and ice dust mixtures provided empirical data on radiation pressure effects, thermal response, and mechanical stability. By comparing laboratory behavior with observed motion of the swarm, scientists could assess whether known materials, when configured in unusual ways, could account for anomalies. In many cases, laboratory results suggested that ordinary materials under extreme interstellar conditions could produce effects resembling those observed, reinforcing the idea that exotic behavior does not necessarily require entirely new physics, but may arise from uncommon configurations of familiar substances. The consideration of exotic matter also had implications for the swarm's formation and survival. Highly porous or low-density structures are fragile and sensitive to collisional disruption, yet the 3I Atlas companions retained coherence over interstellar distances. This implied that the objects either formed in a low-collision environment or were stabilized by internal structure or self-gravity, highlighting the delicate balance required for survival during ejection from a parent system and subsequent interstellar transit. The resilience of the swarm thus became a clue to both composition and history, linking material properties with long-term dynamical stability. Furthermore, compositional anomalies suggested that the companions might carry information about their origin environment. Differences in spectral features, reflective properties, and thermal behavior could reflect distinct regions within a parent body or exposure to variable radiation fields during interstellar travel. If true, the swarm becomes not merely a set of moving objects but a repository of astrophysical history, encoding chemical, physical, and dynamical information that can be decoded through careful observation and modeling. Each deviation from expected behavior offers a potential data point for reconstructing the conditions of formation, ejection, and interstellar journey. The exotic matter hypothesis also intersected with speculative astrophysics. Concepts such as unusual ice-metal mixtures, volatile rich composites, or charged dust aggregates extend beyond traditional comet and asteroid models, but remain within the bounds of physical plausibility. These frameworks allow the combination of multiplicity, alignment, non-gravitational acceleration, and spectral heterogeneity to be interpreted as emergent properties of specific material configurations rather than requiring fundamentally new forces or laws. By integrating observational data with theoretical modeling, scientists could explore a spectrum of compositions capable of reproducing key anomalies, balancing empirical evidence with creative interpretation. Finally, the exploration of exotic matter underscores the iterative nature of modern astrophysical inquiry. Observations inform simulations. Simulations suggest potential compositions. Laboratory experiments test feasibility, and subsequent observations refine both models and hypotheses. In the case of 3I Atlas, the swarm's unusual behavior, multiplicity, alignment, acceleration, and spectral diversity serves as a focal point for this cycle. pushing the boundaries of knowledge while remaining anchored to measurable phenomena. The consideration of exotic matter thus exemplifies the synergy of observation, theory, and experiment, illustrating how astronomers probe the unknown, translating faint interstellar signals into rich insights about composition, dynamics, and the subtle forces that shape celestial systems. As 3I Atlas and its companions moved closer to the inner solar system, astronomers began to focus on the temporal dynamics of the swarm, investigating how their velocities and trajectories changed over time and what these changes revealed about underlying forces and histories. Unlike stable solar system objects, whose orbits are well-defined and slowly varying, interstellar bodies traverse space with hyperbolic velocities, often interacting weakly with the solar environment. Temporal analysis thus became crucial to understanding both the immediate motion of the companions and the cumulative influences of interstellar travel on their dynamics. High-cadence observations allowed precise measurement of velocity changes over intervals of hours, days, and weeks. By comparing predicted positions from earlier models with actual observations, astronomers detected subtle variations in speed and direction among companions. Some objects appeared to accelerate slightly as they approached the Sun, while others exhibited minor decelerations, hinting at forces beyond classical gravity. These temporal variations correlated with spectral and photometric data, suggesting connections between material properties, radiation pressure, and sublimation of volatile compounds. By integrating temporal dynamics with compositional analysis, scientists gained a richer understanding of how interstellar objects interact with the solar environment. The staggered arrival times of the companions provided additional insight. While initially observed as a group, careful analysis revealed that each companion reached perihelion at slightly different intervals. This spread in timing could reflect initial ejection conditions from a parent body, variations in trajectory through the interstellar medium, or differences in mass and surface properties that influence the cumulative effect of non-gravitational forces. By modeling these factors, astronomers could reconstruct plausible scenarios for the swarm's dispersal and alignment, connecting temporal patterns with physical and dynamical characteristics. Temporal variation also illuminated rotational and structural effects. Photometric light curves revealed periodic fluctuations in brightness, indicative of rotation or tumbling. These rotational states influenced how companions interacted with radiation pressure and thermal forces, producing subtle accelerations that varied over time. By correlating rotational periods with observed motion, researchers could assess how spin dynamics contributed to trajectory deviations. This temporal dimension added complexity, but also explanatory power, linking observed anomalies to measurable physical characteristics. Cumulative effects of solar radiation became increasingly important as the companions approached the inner solar system. Radiation pressure and solar wind interactions, while negligible at interstellar distances, grew in influence closer to the Sunday. The impact of these forces was time-dependent, with acceleration accumulating gradually over days and weeks. By monitoring the evolution of hyperbolic velocities, astronomers could estimate the magnitude of radiation-induced effects and compare them with predicted outgassing contributions. These analyses reinforced the notion that even weak forces acting over temporal scales could produce observable deviations in hyperbolic motion. Temporal analysis also revealed subtle correlations among companions. While individual accelerations varied, small groups exhibited synchronous changes in velocity or alignment, suggesting either weak gravitational interactions or shared responses to external forces such as solar radiation or interstellar medium influences. Detecting these correlations required precise timing and repeated observation, emphasizing the importance of global coordination among observatories. The resulting temporal data provided a dynamic portrait of the swarm, capturing not only static positions but evolving motion across both space and time. Simulations incorporating temporal dynamics allowed researchers to test hypotheses regarding swarm origin and behavior. Fragmentation models, for instance, could reproduce staggered arrival times and differential acceleration if initial conditions included variation in fragment ejection, velocities, and rotation. Interstellar cloud scenarios, in which loosely associated objects gradually converged, also accounted for temporal dispersal patterns, though alignment consistency required fine-tuning. By comparing model outputs with observed temporal sequences, scientists could assess the plausibility of various formation and ejection mechanisms, refining understanding of how interstellar processes produce multiplicity and coherence. The temporal behavior of the companions had implications for potential interactions with Mars and other planetary bodies. By projecting motion over days and weeks, astronomers could predict close approaches, gravitational perturbations, and relative positions among companions. These forecasts informed observational scheduling, ensuring that telescopes captured critical moments when subtle interactions were most pronounced. Temporal modeling also allowed assessment of cumulative effects. Small accelerations, while negligible over hours, could lead to measurable deviations in predicted positions over days, offering a window into both physical properties and environmental influences. Observing the temporal evolution of acceleration and alignment highlighted the interplay between predictability and uncertainty. While simulations could reproduce broad patterns, minor deviations persisted, suggesting unmodeled forces or heterogeneity in companion properties. This tension exemplifies a recurring theme in interstellar studies. Even with extensive data and sophisticated modeling, complexity arises from the interplay of multiple subtle influences over time. The companion's motion thus provides a tangible illustration of how deterministic physical laws combine with probabilistic interactions to produce observable phenomena that are both ordered and enigmatic. Finally, the temporal dynamics invite philosophical reflection on the nature of interstellar travel. Each companion's path represents a journey spanning millions of years, influenced by forces too weak to perceive directly, yet capable of accumulating measurable effects. Their staggered arrivals, varying velocities, and evolving alignment reveal the subtle choreography of interstellar motion, a dance governed by both deterministic physics and cumulative chance. Observing these temporal patterns allows humanity to glimpse processes operating on scales of time and distance far beyond human experience, offering insight into the long-term evolution of matter and energy in the galaxy. In summary, the analysis of temporal behavior among three I-Atlas companions provided crucial insights into their dynamics, physical properties, and potential origins. By integrating observations across hours, days, and weeks, astronomers could quantify subtle accelerations, rotational effects, and interobject correlations, linking temporal variation to compositional and structural characteristics. These insights informed both theoretical modeling and observational strategy, highlighting the value of continuous monitoring and multidisciplinary analysis. At the same time, the evolving motion of the swarm evokes reflection on the delicate interplay between physical law, cumulative forces, and the vast scales of interstellar space, revealing a universe where time itself shapes the story of matter in motion. As the swarm of three I-Atlas companions continued its passage toward the inner solar system, attention increasingly focused on potential observational opportunities from space-based platforms. Ground-based telescopes, while critical, faced limitations imposed by atmospheric interference, daylight cycles, and weather conditions. Spaceborne instruments offered unparalleled stability and sensitivity, enabling detection of fainter companions, precise measurement of spectral features, and continuous monitoring of dynamic behavior. Satellites, such as the Hubble Space Telescope, Spitzer, and smaller survey missions, were tasked with capturing both positional and compositional data, providing a comprehensive view of the swarm as it neared Mars. High-resolution imaging from Hubble allowed astronomers to resolve individual companions that appeared as mere points of light in ground-based observations. By employing long exposure times and advanced image stacking techniques, Hubble's instruments revealed subtle variations in brightness and apparent size, critical for estimating shape, rotation, and albedo. Observations indicated that some companions were elongated or irregular, while others appeared more spheroidal, suggesting differences in formation or collisional history. These morphological insights were integrated with orbital and spectroscopic data, producing multidimensional profiles for each object, essential for testing hypotheses about origin, evolution, and non-gravitational forces. Infrared monitoring from Spitzer and other space-based platforms added thermal characterization to the observational toolkit. By measuring heat emission from the companions, scientists could infer size, composition, and surface roughness with greater precision than visible light observations alone. Variations in thermal properties between companions suggested heterogeneity in material composition, consistent with spectral data indicating both rocky and icy surfaces. Thermal modeling also helped quantify the effects of radiation pressure and sublimation, linking physical characteristics to observed deviations in motion. This synthesis of optical, spectral, and thermal data provided a more complete understanding of the swarm's physical state. Space-based spectroscopy further enhanced compositional analysis. By observing across multiple wavelengths free from atmospheric absorption, satellites provided clear signatures of minerals, ices, and organic compounds. Some companions displayed spectral features consistent with silicate-rich surfaces, while others exhibited absorption bands indicating frozen volatiles such as water, carbon monoxide, or ammonia. The diversity in composition reinforced earlier hypotheses of either a differentiated parent body or independent origins for individual companions. Moreover, the spatial correlation of spectral types with minor clustering patterns suggested that fragmentation or environmental exposure might have produced systematic variation, offering insight into the physical processes shaping interstellar debris. Continuous observation from orbit also enabled monitoring of dynamic behavior on short timescales. Light curve analysis captured rotation periods and tumbling motions, revealing irregular spin states among several companions. These rotational dynamics contributed to the swarm's non-gravitational accelerations, as uneven exposure to solar radiation and sublimation created time-dependent thrust. By combining orbital data with rotational characterization, scientists refined models of motion, accounting for subtle variations in velocity and trajectory that ground-based observations alone could not resolve. The integration of temporal and rotational data underscored the importance of high-cadence, uninterrupted monitoring in understanding interstellar object dynamics. Space-based platforms facilitated predictive modeling for near-approach events with Mars. By projecting trajectories using high-precision astrometry, researchers could forecast close passages, estimate gravitational deflections, and assess opportunities for coordinated observation with Martian orbiters. These predictions guided telescope scheduling, ensuring that the brightest or most scientifically significant companions were captured during critical windows. Observing interactions with Mars's gravitational field, even at distances of millions of kilometers, allowed refinement of mass and density estimates, providing constraints on physical models of the swarm. The data from space telescopes also helped constrain hypotheses about exotic material properties. High-resolution imaging, thermal emission, and spectral signatures collectively tested models involving low-density aggregates, reflective surfaces, or compositional heterogeneity. By comparing observational results with predictions from simulations incorporating radiation pressure, outgassing, and interstellar environmental forces, scientists could evaluate the plausibility of various material scenarios. In some cases, observed anomalies in acceleration or alignment were consistent with the presence of low-density, highly reflective structures, supporting earlier speculative frameworks while leaving room for further investigation. Additionally, space-based observation enabled cross-validation of ground-based measurements. Comparing data from orbiting instruments with terrestrial telescopes allowed identification of systematic errors, calibration inconsistencies, and observational biases. This validation enhanced confidence in derived orbital parameters, spectral classification, and thermal properties, ensuring that conclusions drawn from combined datasets reflected true physical behavior rather than instrumental artifacts. The synergy between spaceborne and ground-based observation exemplified modern astronomical methodology, demonstrating the necessity of multi-platform, multi-wavelength approaches for studying faint, fast-moving interstellar phenomena. The comprehensive observational campaign also revealed emergent patterns in the swarm's behavior. Temporal analysis indicated correlated acceleration trends among subgroups, suggesting weak mutual gravitational interaction or coherent response to external forces such as radiation pressure. Spatial clustering persisted, albeit gradually dispersing as companions approached Mars and experienced differential perturbations. The combination of continuous monitoring and high-precision data allowed researchers to distinguish between intrinsic physical effects and environmental influences, producing a nuanced understanding of swarm dynamics. Philosophically, the ability to observe these companions from space emphasized humanity's capacity to extend perception across vast distances. From Earth orbit, satellites captured light emitted or reflected billions of kilometers away, resolving structures and behaviors invisible to the naked eye. This capability transformed points of light into dynamic, measurable entities, each encoding information about composition, motion, and interstellar history. Observing the swarm in such detail reinforced both the fragility and resilience of matter traveling across the galaxy, highlighting the subtle interactions that shape trajectories over millions of years and billions of kilometers. In summary, space-based observation provided a critical complement to ground-based efforts, enabling high-resolution imaging, multi-wavelength spectroscopy, thermal characterization, and continuous temporal monitoring. These data refined models of orbital dynamics, material properties, and rotational behavior, informing both theoretical simulations and predictive analyses. The combination of spaceborne and terrestrial observations created a comprehensive portrait of the swarm, revealing subtle correlations, emergent patterns, and material diversity. By extending observational reach beyond Earth's atmosphere, scientists gained an unprecedented window into interstellar phenomena, bridging empirical measurement with theoretical insight and illuminating the complex interplay of forces shaping the motion and composition of 3I Atlas and its companions. As 3I Atlas and its companions advanced through the inner solar system, attention shifted to the potential implications for planetary defense, interstellar dust delivery, and even the origin of prebiotic materials. While the objects posed no immediate threat to Earth or Mars due to their hyperbolic trajectories, their passage offered an unprecedented opportunity to study the transfer of matter across interstellar distances. Scientists began to consider how such bodies, through both their bulk composition and the fine dust they carried, might interact with planetary atmospheres, influence chemical environments, or contribute to the broader galactic cycle of matter. The consideration of potential planetary impact risk, while remote, remained an important aspect of the analysis. Each companion's trajectory was precisely modeled, incorporating perturbations from planetary gravity, radiation pressure, and observed accelerations. Monte Carlo simulations explored a wide range of possible deviations, assessing the probability of rare but consequential near-collision events. Results consistently indicated that direct impacts were exceedingly unlikely. The swarm's hyperbolic velocities ensured that most companions would pass through the solar system on trajectories largely uninfluenced by planets. Yet even near-miss encounters offered opportunities for scientific observation, particularly in measuring gravitational deflection, tidal effects, or subtle variations in velocity induced by planetary mass. Beyond immediate collision considerations, the swarm provided a natural laboratory for studying the delivery of interstellar material to planetary environments. As the companions approach the inner solar system, sublimation of volatile compounds releases dust and gas, producing microparticles that drift along trajectories influenced by solar radiation and planetary gravitational fields. This process mirrors, on a smaller scale, the hypothesized delivery of prebiotic materials by comets and interstellar objects in the early solar system. By observing the composition and behavior of these ejected particles, scientists gain insight into the types of matter that can traverse interstellar distances and potentially seed planetary environments with chemical building blocks. The potential for chemical enrichment is particularly compelling. Spectroscopic observations indicate that the companions carry ices containing water, carbon monoxide, and other volatile molecules, along with silicate-rich material and possible organics. As sublimation occurs, these materials enter the local interplanetary environment, allowing measurement of particle distribution, composition, and interaction with solar radiation. Such data help constrain models of chemical transport across the galaxy, informing hypotheses about the origin of prebiotic compounds on Earth and other planets. Observing these processes in real time offers a rare window into mechanisms that, until now, could only be inferred from meteoritic studies and laboratory simulations. Planetary atmospheres themselves serve as natural detectors of interstellar material. As dust and gas are released from companions, some particles may be gravitationally captured or interact with tenuous atmospheric layers, producing measurable signatures in spectral absorption, ionization, or transient auroral phenomena. While the mass flux is minimal compared to typical solar system meteor activity, precise instruments on orbiters such as MAVEN, Mars Reconnaissance Orbiter, and Earth-orbiting satellites can detect subtle anomalies. These observations allow for direct study of interstellar material in situ, providing empirical data on particle size distribution, chemical composition, and interaction with planetary environments. The swarm also offered insights into the dynamics of dust dispersal in space. The companion's hyperbolic motion, coupled with rotational dynamics and surface heterogeneity, produces anisotropic ejection of dust and gas. By modeling the trajectories of individual particles, scientists can investigate the cumulative effect of small-scale forces, including solar radiation pressure, Lorentz forces from interplanetary magnetic fields, and weak gravitational influences. Such models inform broader understanding of how interstellar dust propagates, aggregates, or decays over interstellar and interplanetary distances, linking microscale physical processes to large-scale galactic phenomena. Temporal analysis of dust ejection became increasingly critical as the companions approached Mars. By correlating rotational light curves, sublimation rates, and orbital deviations, researchers could model the timing and distribution of particle release. These temporal dynamics revealed variations among companions. Some exhibited steady, low-level ejection, while others showed episodic bursts, possibly linked to rotational orientation, surface heterogeneity, or transient exposure to solar heating. Understanding these patterns allows for more accurate modeling of particle trajectories and potential observational opportunities from orbiting spacecraft or ground-based detectors. Spectroscopic monitoring of ejected material provided further insight into chemical composition. High-resolution measurements indicated the presence of water, ice, carbonaceous compounds, and silicate dust, consistent with the inferred composition of the bulk objects. Minor variations among companions suggested differential surface processing or compositional heterogeneity within a parent body. These observations support the notion that interstellar objects can carry complex, chemically diverse matter, providing a medium for chemical enrichment of planetary systems over galactic timescales. The implications extend beyond immediate observational science. By studying how interstellar objects like 3I Atlas interact with planetary environments, astronomers gain insight into the long-term evolution of chemical reservoirs in planetary systems. Each passage represents a natural experiment in matter transport, revealing processes that may have contributed to the delivery of water, organics, and other volatiles to nascent planets. In this sense, the swarm not only illuminates the dynamics of interstellar motion, but also provides a tangible link between cosmic-scale processes and planetary habitability, highlighting the interconnectedness of celestial phenomena across space and time. Finally, these observations emphasize the broader philosophical context of interstellar study. The companions' motion, dust ejection, and interaction with planetary environments illustrate the subtle exchange of matter across vast distances, revealing a universe in which even small objects participate in cosmic processes of distribution and transformation. Studying these processes allows humanity to trace threads connecting distant star systems to our own planetary neighborhood, offering both scientific insight and contemplative reflection on the scale, connectivity, and dynamism of the cosmos. In observing 3I Atlas, astronomers witness not merely objects in motion but the active flow of material and energy through the galaxy, a silent narrative linking origin, transit, and interaction across unimaginable scales. As the companions of 3I Atlas approached the vicinity of Mars, astronomers began to consider the cumulative gravitational effects of the planet on the swarm. While individual companions were small and low in mass, the precise monitoring of their hyperbolic trajectories revealed minute deflections as they passed near planetary fields. These deflections, though subtle, provided critical data for refining estimates of mass, density, and rotational dynamics for each object. By carefully modeling the interactions between the swarm and Mars's gravitational influence, researchers gained insight not only into the immediate motion of the companions, but also into the broader mechanisms that govern interstellar object dynamics in planetary systems. To analyze these interactions, high-precision N-body simulations were employed. Each companion was represented as a discrete particle, incorporating estimates of mass, rotation, and surface properties. The simulations included gravitational forces from the Sun, Mars, Jupiter, and other relevant planetary bodies, while also integrating non-gravitational forces such as radiation pressure and potential outgassing. By running multiple iterations with slight variations in initial conditions, astronomers could assess the sensitivity of the swarm's motion to planetary perturbations, identifying patterns of deflection and velocity change that corresponded to specific physical characteristics. The approach of Mars offered an observational advantage. The relatively close proximity allowed for high-resolution astrometry, enabling measurement of positional shifts at unprecedented precision. Instruments aboard Mars orbiters, including the Mars Reconnaissance Orbiter's high-rise camera and MAVEN's atmospheric detectors, provided complementary data to ground-based and spaceborne telescopes. These measurements allowed scientists to detect deviations as small as a few meters per second in velocity and arcseconds in position. Even such minor shifts held significance, offering clues about the mass distribution and structural properties of individual companions. Observations revealed that some companions experienced slight accelerations as they passed near Mars, consistent with gravitational slingshot effects, while the hyperbolic velocities of the swarm ensured that no object would be captured by Mars. The transient gravitational influence produced measurable changes in trajectory. By comparing observed deviations with predicted values from simulations, astronomers could refine estimates of bulk density and rotational states. For instance, objects with low density and high porosity were more susceptible to subtle deflections due to variations in surface orientation and internal structure, offering indirect evidence for exotic or unusual material composition. Beyond individual deflections, the swarm's collective motion exhibited emergent behavior during the Mars flyby. Some companions showed transient clustering, as slight gravitational convergence produced temporary alignments. These ephemeral patterns provided a unique opportunity to study weak multi-body interactions under interstellar conditions, revealing how even minimal gravitational coupling among low-mass bodies can influence trajectories when compounded over astronomical distances. The observation of such effects reinforced the notion that multiplicity introduces complexity far beyond what would be expected for solitary interstellar objects. Thermal and rotational dynamics further modulated the swarm's response to Mars's gravitational field. Photometric light curves indicated that several companions were tumbling or spinning irregularly. The combination of rotation and varying albedo produced differential radiation pressure effects, which, when superimposed on gravitational deflection, resulted in complex, time-dependent deviations in trajectory. By integrating rotational states and surface characteristics into N-body simulations, astronomers were able to reproduce many of the observed anomalies, demonstrating the interplay between internal physical properties and external forces in shaping motion. The temporal resolution of the observations was critical for capturing these dynamic effects. High-cadence imaging allowed astronomers to track subtle accelerations and positional changes over intervals of hours, revealing patterns that would be undetectable with sparse observation. By mapping the evolution of velocity and alignment, researchers could correlate specific deflections with rotational orientation, surface reflectivity, and proximity to Mars. This temporal mapping provided a multi-dimensional understanding of swarm dynamics, linking moment-to-moment behavior with broader orbital trends. The Mars encounter also prompted reflection on the potential cumulative effects of planetary perturbations over multiple interstellar passages. While the companions' hyperbolic trajectories ensured they would not be captured, repeated interactions with planetary fields over successive stellar systems could gradually modify velocities, spin states, and orientation. This perspective offered a framework for understanding how interstellar objects evolved dynamically over millions of years, influenced not only by forces within their origin systems, but also by repeated encounters with planetary and stellar environments throughout the galaxy. Spectroscopic and thermal observations during the Mars approach added further depth. Minor variations in reflected light and infrared emission suggested that proximity to the Sun and planetary radiative effects could induce sublimation or surface modification. For some companions, the brief increase in solar irradiation during inner solar system transit may have triggered episodic outgassing, producing additional small accelerations. These effects, combined with gravitational deflections, contributed to the complex motion observed and highlighted the interplay of multiple forces acting simultaneously on low-mass interstellar bodies. Finally, the Mars flyby provided a natural laboratory for testing predictive models of interstellar object dynamics. By comparing observed deflections and accelerations with simulations that incorporated mass, density, rotation, and non-gravitational forces, scientists could validate or refine their theoretical frameworks. The high precision of observational data allowed for constraints on previously uncertain parameters, including bulk density, rotational state, and surface heterogeneity. The encounter thus served both as an observational milestone and as a critical validation point for models seeking to explain the swarm's behavior. In sum, the interactions between 3I Atlas companions and Mars illuminated the subtle interplay of gravitational, rotational, and non-gravitational forces shaping interstellar object dynamics. High-resolution observation and sophisticated simulation revealed not only deflections and accelerations, but also emergent clustering and transient alignment patterns. The Mars flyby demonstrated how even low-mass companions, moving at hyperbolic velocities, are influenced by planetary fields in ways that provide insight into internal structure, composition, and long-term dynamical evolution. By combining empirical observation with theoretical modeling, astronomers captured a vivid, multidimensional portrait of interstellar swarm dynamics, offering a glimpse into processes that operate on scales far beyond human experience and highlighting the delicate balance of forces governing motion across the cosmos. The increasing proximity of 3I Atlas and its companions to the inner solar system prompted scientists to explore potential interactions with interplanetary magnetic fields and the solar wind. While the swarm's hyperbolic velocities ensured that gravitational capture by planets was improbable, the interplanetary environment introduced subtle electromagnetic effects capable of influencing low-mass, highly responsive bodies. Charged particles, solar radiation, and magnetic fields collectively produced forces that, while weak compared to gravity, accumulated over the approach, contributing to the nuanced accelerations and minor trajectory deviations observed in several companions. Space-based measurements of the solar wind and interplanetary magnetic field provided critical input for these analyses. Instruments aboard satellites, such as ACE, Advanced Composition Explorer, SOHO, Solar and Heliospheric Observatory, and the Parker Solar Probe, monitored particle flux, magnetic field orientation, and solar activity levels. By integrating this data with the orbital and rotational parameters of the swarm, researchers could simulate the cumulative impact of electromagnetic forces on each companion. Objects with high surface area to mass ratios, irregular shapes, or conductive surfaces were especially susceptible, experiencing minute, directional accelerations that complemented gravitational and radiation-driven forces. The consideration of electromagnetic interactions highlighted the importance of charge accumulation on companion surfaces. Cosmic rays and solar ultraviolet radiation can ionize surface molecules, producing net surface charge. This charge interacts with the solar magnetic field, generating Lorentz forces that influence motion. While extremely small on short timescales, These forces act continuously over days and weeks, producing measurable deviations in hyperbolic trajectories. By modeling charge accumulation and distribution, scientists could account for some of the residual anomalies in velocity and alignment that classical, gravitational, and radiation pressure models could not fully explain. Thermal interactions with the solar wind also contributed to subtle dynamics. The swarm's surface temperatures, influenced by proximity to the Sun, affect material sublimation and outgassing. Ejected gas molecules can produce thrust, modifying both velocity and spin. Combined with electromagnetic interactions, these processes result in a complex, multifactorial influence on motion. By integrating thermal models with plasma physics, researchers developed simulations that captured the cumulative effect of radiation, solar wind, and electromagnetic forces, producing results that aligned more closely with observed deviations among companions. Observational evidence supporting these effects emerged from high-resolution tracking of minor velocity variations. Some companions exhibited accelerations inconsistent with gravitational and radiation pressure models alone. By correlating these deviations with solar wind conditions and magnetic field orientation, astronomers inferred that electromagnetic forces contributed measurably to the swarm's dynamics. Although subtle, these influences reinforce the notion that interstellar objects are not entirely immune to interplanetary environmental effects, even at velocities exceeding tens of kilometers per second. The interplay of electromagnetic forces with rotation added further complexity. Rotating or tumbling companions expose varying surface areas to solar wind and magnetic fields over time, producing periodic accelerations or torque. Photometric light curves and high-cadence observations revealed rotation periods ranging from hours to days, suggesting that spin dynamics modulate electromagnetic interactions in a time-dependent manner. Incorporating rotational states into models improved the match between observed and simulated motion, highlighting the multi-dimensional nature of forces acting on small interstellar bodies. The swarm's approach offered a natural experiment for studying these interactions. Unlike isolated interstellar objects, the multiplicity of companions allowed comparative analysis, revealing how variations in size, composition, and rotation influence response to solar wind and magnetic fields. Some companions, particularly low-density or highly reflective ones, displayed larger deviations, while others remained more inertial. By examining these differences, researchers could infer correlations between material properties and susceptibility to interplanetary forces, advancing understanding of how interstellar bodies interact with their environment. In addition to influencing trajectories, electromagnetic interactions carry implications for the swarm's long-term evolution. As companions exit the inner solar system, cumulative effects from solar wind and magnetic fields can alter spin, rotation, and surface properties. Over interstellar timescales, repeated interactions with stellar environments, cosmic rays, and galactic magnetic fields could further modulate trajectories and alignment, affecting multiplicity patterns and clustering in subsequent encounters. Observing these processes in real time offers empirical grounding for models of interstellar object evolution across millions of years. Spectroscopic observations complemented these studies by revealing subtle changes in surface composition consistent with charged particle interactions. Minor modifications in absorption features suggested surface alteration due to ion bombardment or sputtering, confirming that the interplanetary environment exerts measurable influence on interstellar matter. Coupled with rotational and thermal data, these observations painted a multidimensional portrait in which electromagnetic, gravitational, and radiation-driven forces interact to shape both motion and surface characteristics. Finally, the study of electromagnetic effects emphasized the interconnectivity of cosmic scales. The companion's trajectories, shaped by forces originating billions of kilometers away, reveal how the interstellar medium, solar wind, and planetary fields collectively influence small bodies. These observations underscore the principle that even in seemingly empty space, interactions are continuous and cumulative, linking the microphysics of particle interaction with the macroscopic motion of objects across interstellar distances. The swarm thus serves as both a laboratory and a messenger, illustrating the subtle, pervasive influence of electromagnetic and plasma processes in shaping the motion and evolution of interstellar matter. As the swarm of 3I Atlas companions progressed deeper into the inner solar system, scientists turned their attention to potential observational signatures of outgassing and volatile release. While the companions were too small and distant to produce the dramatic coma typical of solar system comets, high-sensitivity instruments revealed subtle emission lines and photometric anomalies consistent with the sublimation of ices. These emissions, though faint, offered critical insight into both composition and dynamic behavior, linking physical processes at the microscopic level with macroscopic motion and providing additional constraints for models of non-gravitational acceleration. Spectroscopic measurements captured weak emission features in the ultraviolet and visible spectrum, indicative of molecular species such as H2O, CO, and CO2. By comparing the intensity and temporal variability of these lines across multiple companions, astronomers could infer differences in volatile abundance, surface area exposure, and sublimation efficiency. Some companions exhibited nearly constant emission rates, suggesting a uniform distribution of ices across the surface, while others displayed episodic bursts, potentially linked to rotation or transient solar heating of previously shadowed areas. These observations provided a tangible mechanism for subtle accelerations as outgassing produces directional thrust capable of influencing hyperbolic trajectories. Infrared observations complemented the spectroscopic data, capturing thermal signatures of sublimating surfaces. By measuring infrared flux, researchers estimated temperature distributions across each companion, identifying regions where solar heating exceeded sublimation thresholds. Variations in thermal emission were correlated with light curve data to deduce rotational orientation and periods, revealing how spinning bodies modulate